Comrades, briefers are sort of the dear Abbey of Flightum. They will answer almost any question, about aviation that is. Questions about your love life should still be directed to Dear Abbey. They'll tell you about customs, search and rescue, ATC services, preferred routes, and why the computer will take flight plans for one route and not another. They will look up phone numbers for aviation facilities, not your Aunt Maud in Minneapolis. Read Class D notams provide information about military training routes, restricted areas, and other special use airspace. They will do almost anything they can to get you almost any information you want about the aviation system. Just ask, and ye shall receive.
Other sources of weather information. There is, the proverb says, more than one way to skin an aeroplane, and there are lots of other places to get information about which way the clouds blow. Newspapers. My uncle liked his newspaper because he could swat the dog with it when the little fella did something wrong. It's no wonder the newspaper started turning up wet. That also explains why the dog started chasing the paper boy. Nevertheless, the paper provides you with some valuable information about weather. Most newspapers publish a weather map showing major weather systems around the country, and many carry a satellite picture which helps provide a look at what the weather's doing. Weather-wise pilots study weather on a daily basis. Simply take the weather chart and/or satellite photo provided by the paper and examine it every day. These charts are a lot more accurate than they were several years ago. You'll be surprised how weather-savvy you'll become with this small investment of time. PATWAS, PATWAS, or Pilot's Automatic Telephone Weather Answering Service, is a continuous recording of weather and aeronautical information for pilots. It's provided by non-automated flight service stations and contains a summary of information for areas within 50 nautical miles of the parent station. PATWAS is not intended as a substitute for a briefing by a flight service station specialist. It is, however, useful as a preliminary briefing to help in making those go or no-go decisions. Phone numbers for PATWAS are available by calling your local flight service station. Telephone Information Briefing Service, TIBS. TIBS is a continuous telephone briefing service consisting of pre-recorded weather information. It's offered by automated flight service stations and provides weather briefings for an area or a route. It also provides airspace procedures and special aviation announcements. Using your touch-tone phone, you can select from several weather menus of pre-recorded information. You have the option, at any time, of transferring directly to a live briefer. Transcribed Weather Broadcast, TWEB. A TWEB is a pre-recorded broadcast of weather and aeronautical information by selected flight service stations. Broadcast continuously over selected navigation stations, like VORs and NDBs, TWEBs contain information on route-oriented weather. They usually provide information for a corridor 25 miles to either side of a specified route along which certain broadcasting navaids are located, VOR airways, for instance. Figure 3 shows a VOR frequency box with a small blue circle containing a reverse bold T in its corner. This means that a TWEB broadcast is available on the VOR. Some TWEB broadcasts can be accessed by telephone. These broadcasts are intended to supplement your in-flight weather information and are not intended as a substitute for a specialist-provided briefing. Hazardous In-Flight Weather Advisory Service, HIWAS, HIWAS. HIWAS is a continuous broadcast of in-flight weather advisories. Similar to TWEBs, HIWAS can be received over certain VOR and NDB stations, Figure 4. The purpose of HIWAS is to keep you abreast of any hazardous weather, such as thunderstorms, icing, strong winds, etc. These advisories of hazardous forms of weather are sometimes called SIGMETs or ERMITs, and will be discussed in more detail later. The unique thing about HIWAS, as well as TWEBs, is that you can simply turn up the volume on your VOR and listen to this continuous weather broadcast while traveling to your destination. This keeps you informed without having to repeatedly contact the flight service station. In a geographical area where HIWAS has been implemented, you might hear a HIWAS alert on an ATC frequency, such as approach or departure control. The alert notice might sound like this. Attention all aircraft, monitor HIWAS or contact a flight service station on frequency 122.0 or 122.2 for new convective SIGMET information. Upon hearing this one-time alert, you should make plans to contact the flight service station to find out if this information is applicable to you. At least listen to the nearest VOR over which HIWAS is broadcast for a description of the particular weather information contained in the alert notice. As with all pre-recorded in-flight broadcasts, HIWAS is not intended as a substitute for a specialist-provided briefing. Take advantage of these in-flight weather advisories by keeping the volume up slightly when using a TWEB or HIWAS broadcasting navigation station. When you hear any voice transmission, turn up the volume to listen to the incoming broadcasts. En route Flight Advisory Service, EFAS. EFAS, En route Flight Advisory Service, otherwise known as Flight Watch, is one of the most amazing sources of in-flight weather information available to pilots. It's basically a clearinghouse for timely and meaningful weather information useful to pilots in the air. Flight Watch consists of trained specialists at selected flight service stations who have attended additional weather courses in order to be able to better assist pilots in flight. Flight Watch is the same everywhere, 122.0 MHz. Service is available from 6 a.m. to 10 p.m. local time for aircraft flying between 5,000 feet AGL and 18,000 feet AGL. This service is strictly a weather information service. It's not intended for changes of flight plan information, radar information, or any other non-weather-related activity. Because EFAS covers a rather large area, remote communication outlets have been established to assist pilots in reaching the Flight Watch specialist. Figure 5 depicts the remote communications locations for the Albuquerque Flight Service Station. If you are near Guadalupe Pass and wanted to communicate with Flight Watch, simply transmit on 122.0 MHz and say, Albuquerque Flight Watch, Cessna 2132 Bravo, Guadalupe Pass, over. The EFAS specialist will transmit on the remote transmitter and receiver located in the area of the Guadalupe Pass. If you don't know the name of the flight service station or remote facility, simply call and tell them what VOR you're near. For instance, you might say, Flight Watch, this is Cessna 2132 Bravo, Millard VOR, over. This tells the specialist which remote transmitter to activate to talk to you. Imagine if you called Albuquerque EFAS and just said, Albuquerque Flight Watch, this is 2132 Bravo, over. The specialist would have to switch through all those remote transmitters saying, 32 Bravo, you there? Are you on this one? 32 Bravo, can you hear me now? 32 Bravo, click. 32 Bravo, click. 32 Bravo, click, click, click. Pilot Reports, PIREPs. One of the problems with the weather is that it changes. Weather forecasting is a game of catch-up that can never be won. The closest you can come is pilot reports, PIREPs, P-I-R-E-P-S, which represent actual information on current conditions as reported by pilots in the air. These reports are made to the flight service station, EFAS, or an ATC facility, and they can be of immense assistance in helping you to make a go, no-go decision, or to avoid problem areas once you're airborne. When contacting EFAS or the flight service station in flight or before takeoff, you will usually be provided current pilot reports as part of the weather briefing. If they aren't forthcoming, ask for them. These reports give you a good idea as to how closely reality is to the forecast. In many cases, PIREPs have allowed me to make a decision to go when the forecast painted a very bleak picture. PIREPs become especially important in understanding what's happening in areas where weather reporting stations are few and far between. Near the end of this chapter, I'll show you how to decode PIREPs transmitted by the flight service station. Whenever you contact the flight service station, EFAS or ATC, give them a pilot report. Pilots don't do this often enough. Even if the weather is clear, report it. I make it a point to listen to the ARTCC, the Air Route Traffic Control Center, whenever I'm on a cross-country flight, whether or not I'm signed on for radar service. Believe me, if there's nastiness ahead, you'll hear it. My rule is that when the male pilot's voices hit a high C or above, it's time to reevaluate my options. This is one of those cases where it's not just what they say, but how they say it that counts. Weather reports. There are many weather reports available from the National Weather Service and private weather services to aid pilots in flight planning. Knowing what to ask for and how to use the information is an important pilot skill. The available weather products are of two basic types: observations and forecasts. Observations are historical. They are the weather conditions that occurred at the time the observation was taken. Forecasts are weather estimates for several hours, sometimes days, into the future. Like all estimates, weather forecasts are subject to change, sometimes considerable change. If you've ever remodeled your house and remember what the original estimate was and what you finally paid, you understand exactly what I'm saying. Let's examine the weather reports you'll need for successful and safe VFR flight planning. Unless the weather report has the word forecast or prognosis in it, then it's probably an observation.
You know, I was just telling Paulie, even though we live in South Philadelphia, it still gets pretty cold outside. You know, there are some pretty interesting inventions in the world, such as a pager that will summon you when your car's being burglarized, enabling you to get burgled and beat up in the single evening. There is, however, no contraption that will interpret the weather for you. Though if you do a poor job of it, you still might manage to get beat up.
You and only you are responsible for making your go or no-go decisions. It takes training to make good weather decisions. Weather charts are part of this training. There are many times when you'll have access to weather charts without the benefit of an actual briefer. Knowing how to interpret these charts is very important. Most of the following weather charts are on the private pilot knowledge exam. I have added additional practical information where appropriate. You'll find that a few charts have partial legends accompanying them. These legends help interpret some, but not all, of the chart symbols. For purposes of the FAA knowledge exam, you'll need to memorize some basic chart symbology. As you'll soon see, many of the chart symbols can be generalized to other charts. I'll specifically advise you when a chart's legend is available for a specific chart on the exam. New international reports. Aeroplanes have helped shrink the world, and one of the results is an increasing demand for consistency internationally. This is particularly crucial in aviation, where pilots have the capability to cross numerous national borders within a few hours. Because weather is so vital to flight safety, it was agreed internationally that consistency in reporting the weather was desirable. A pilot should be able to look at a weather report anywhere in the world and read it. That's why a new format was introduced in the U.S. on July 1, 1996. What were once called Service Aviation Observations, SAs, and Terminal Forecasts, FTs, are now the METAR, Meteorological Aviation Report, and TAF, TAF, Terminal Aerodrome Forecasts, respectively. METAR, pronounced METAR, as in Eugene. Observations are taken hourly at many reporting stations located across the country. These reports indicate the weather conditions at the time the observation was made. Other than a pilot report, a METAR observation is as close as you can get to the actual weather conditions without sticking your finger out the window. Not only do these reports provide a current weather observation, they also allow you to sense a trend in the weather by observing several of the past hourly reports. Figure 6 shows a typical METAR for several airports. Those reports preceded by the letters SPECI are special, unscheduled reports as a result of a significant weather change. An example would be when the ceiling goes above or below 1,000 feet, or when the visibility goes above or below 3 miles. When you first look at one of these reports, I'm sure it looks as convoluted and cryptic as Egyptian hieroglyphics. Once you learn the code, though, METARs are easy to understand, and learning the weather code symbology from one report often makes the others much easier to learn. You'll notice that these weather reports consist of abbreviations. This is a carryover from the days when weather was sent via teletype, which was slow. Some personal computer software will automatically decode these abbreviations, providing you with a description of the weather in English. Call your local aviation software dealer, and no, you can't use your IBM or Apple computer on the knowledge exam to interpret weather symbols for you. Interpreting the METAR requires an understanding of the individual sections contained within the report. Figure 7 is a breakdown of these individual sections. Let's take a closer look at each one. To better help you understand the order in which a METAR presents the weather, take a look at the following acronym: STWVRWCTDA. This stands for Should Tina walk Vera's rabbit without checking the dog's appetite? Each letter represents a particular segment of the weather contained within the METAR as follows: S. Station identification. T. Time in Zulu or UTC. W. Wind direction and velocity. V. Visibility. R. Runway visual range if reported. W. Weather. C. Clouds. T. Temperature. D. Dew point. A. Altimeter setting. By remembering this acronym, you'll be able to remember the general order in which the information is presented. Keep in mind that a METAR won't report what isn't happening, nor will it report a segment if the measuring equipment, such as a barometer, is not functional. By knowing what should be there, you'll easily identify any missing section. Let's jump into interpreting the METAR. Station. The letter S in Figure 7 represents the first section of the METAR and is a 4-letter stroke number designation for the station or airport reporting this observation. KLAX is the designator for Los Angeles International Airport. K is the international designator that precedes all domestic U.S. location identifiers. Alaska locations start with PA, and Hawaii locations start with PH. You'll learn some of these airport letter designations for your local area as you go along. Besides, some of them are easy enough to guess. The only time you need to be really worried is if you're on an airline flight to Los Angeles and the SkyCap checks your bag with a PKS, Pakistan perhaps, tag. You'll never get it back. Time. The letter T in Figure 7 is the date and time the weather observation was made. For instance, at KLAX, the observation was taken on the 8th day of the month at 1955 Zulu, also referred to as UTC or Coordinated Universal Time. Weather reports are always given in Zulu time. This is the time in Greenwich, England, and not the time certain African tribes use. Using UTC calibrates all the weather reports to one time zone. All you need to do is convert from UTC to your local time zone when interpreting weather reports. Refer to Chapter 14, page N4, to review converting between time zones. Wind. The letter W in Figure 7 identifies the wind direction, velocity, and any gusts. The first 3 digits represent the wind direction in degrees relative to true north. The next 2 digits are the wind velocity in knots, as identified by the letters KT. The G, followed by a number, represents the wind gust in knots. For instance, a wind report of 31015 G27 KT indicates that the wind is 310 degrees at 15 knots with gusts to 27 knots. Gusts are reported when a 10-knot fluctuation occurs between the wind's peaks and lulls. A calm wind is reported as 0.00000 KT. The letters VRB may be used if the wind speed is 5 knots or less. If the wind's direction varies by 60 degrees or more, and the speed is greater than 6 knots, then variable wind direction values follow the reported wind. For instance, a 280V350 following the wind report indicates that the winds are 280 degrees variable to 350 degrees. The 2 extremes in direction will be included in clockwise order. Visibility. The letter V in Figure 7 stands for visibility. Surface visibility is measured in statute miles and fractions thereof. A space divides whole miles and fractions, and the letters SM follow the visibility to indicate statute miles. In Figure 7, the reported surface visibility is 1/2 mile. If you fly internationally, you should be aware that the U.S. is an exception in reporting prevailing visibility for the full 360-degree area of visibility, rather than the lowest sector visibility, which is the international standard. In situations where visibility is very poor in one direction, but fairly good in others, you can be misled by what's prevailing, especially if you're flying in the area where visibility is low. Significant differences in any sector from the prevailing visibility or a differing tower visibility will be stated in the remarks RMK section of the METAR. Runway Visual Range. The letter R in Figure 7 stands for RVR, Runway Visual Range. RVR is an electronically measured value used to determine the distance down a runway that a pilot can see high-intensity runway lights. This shouldn't concern you until you become an instrument-rated pilot. Nevertheless, understand that RVR is measured in feet. Figure 7 shows the RVR along runway 25, R25, is 3,000 feet. The letters L, C, or R that sometimes follow the runway number are designators for the left, center, or right runway. The numbers following the slash indicate the RVR in feet. Weather. The letter W in Figure 7 represents the weather phenomena presently found at the airport. Figure 8 lists the weather codes used in reporting the weather phenomena. These codes contain 5 different columns. The first 2 columns contain qualifiers, intensity or proximity, and a descriptor of the weather. The last 3 columns contain the actual weather phenomena, such as precipitation, obscuration, etc. Up to 3 separate groups of weather phenomena may be included in the report. The most dominant weather is reported first. Precipitation, water products, rain, snow, and hail reaching the surface, are combined into a single group. For instance, moderate rain and snow, these are 2 types of precipitation, present at the airport, is reported as SNRA. Snow is the dominant precipitation and is reported first. Both are types of precipitation and are reported as one group. The absence of a plus or minus sign in front of the precipitation indicates that it's moderate in intensity. Moderate rain, fog, and volcanic ash are 3 separate groups of weather phenomena that are reported as 3 separate groups, RA, FG, VA. If light rain, fog, and volcanic ash were reported, it would look like the following: minus RA, FG, VA. If light drizzle, hail, and a sandstorm were reported, it would look like the following: minus DZ, GR, SS. Remember, light drizzle and hail, both are types of precipitation and are grouped together. It would also be a hail of a weather report. The obscuration or second section of the weather phenomena in Figure 8 is only reported in the weather grouping if the visibility is less than 7 miles. The presence of smoke, FU, at the airport won't be listed in the weather grouping if the visibility is 7 miles or greater. In Figure 7, the letters SHRA represent showers, SH, and rain, RA. This is spoken as moderate rain showers. If it were light rain showers, it would be abbreviated as minus SHRA. Clouds. The letter C in Figure 7 represents the cloud coverage, height, and type. Cloud cover is either SKC, sky clear, indicating no clouds, FEW, few, reporting more than 0 to 2/8 or 2 octaves, SCT, scattered, representing coverage between 3/8 and 4/8 of the sky, BKN, broken, which indicates the sky is between 5/8 and 7/8 covered by clouds, or OVC, overcast, which is complete sky coverage, 8/8 coverage in other words. Automated reporting systems use the letters CLR to indicate no clouds are reported below 12,000 feet. A 3-digit number following the cloud coverage represents the height of the cloud base in hundreds of feet AGL. 3 zeros indicates that the cloud height is less than 50 feet AGL. Cloud types will be provided when towering cumulus, TCU, or cumulonimbus, CB, are observed. Sometimes, weather phenomena based at the surface hide all or part of the sky. This is considered an obscuration. When the sky is obscured and cloud details cannot be assessed, but information on vertical visibility is available, the cloud group is replaced by a 5-character group. The first 2 characters are the letters VV, followed by the vertical visibility in units of hundreds of feet. VV 004 means the vertical visibility is 400 feet. ATIS reports will still broadcast the term indefinite 400 feet obscured. Sometimes an obscuration doesn't obscure the entire sky. In this instance, partial obscurations are reported by the amount of obscuring phenomena: few, scattered, broken, abbreviated FEW, SCT, BKN, followed by 3 digits. In other words, BKN 001. In the remarks, the obscuring phenomena precedes the amount of obscuration, and the 3 digits, in other words, FUBKN 001, which means that the smoke layer at 100 feet AGL is obscuring 5/8 to 7/8 of the sky. From our study of airspace, we know that a minimum of a 1,000-foot ceiling is required for operations within surface-based controlled airspace. In the METAR, the lowest layer of clouds reported as broken or overcast, or any reported vertical visibility into obscuring phenomena, is considered the official ceiling. In Figure 7, the METAR indicates the presence of a 500-foot scattered layer of clouds, a 1,000-foot broken layer of clouds, which is the ceiling, and CBs, or cumulonimbus clouds, are present. Temperature dew point. The letters T and D in Figure 7 represent the reported temperature and dew point in degrees Celsius. This is reported to the nearest whole degree using 2 digits. In other words, 6 degrees C is reported as 06. Sub-zero values are prefixed with an M. For example, 03/M02. In Figure 7, the temperature is 25 degrees C and the dew point is 18 degrees C. Altimeter. The letter A in Figure 7 represents the altimeter setting for that location. The altimeter setting is always prefixed with an A, indicating the altimeter setting in inches of mercury. All 4 digits of the pressure are listed. Simply insert a decimal after the second digit. In Figure 7, the altimeter setting is 30.01 inches of mercury. At the end of the METAR, you will sometimes find supplementary information in the form of remarks, RMK. This is where the briefer can customize his or her weather observation by adding supplemental information. Figure 9 shows a few of these remarks. See the Aeronautical Information Manual or Aviation Weather Services Advisory Circular, AC 00-45D, for more information on remark codes. Don't be overwhelmed. Some of these codes are rarer than a wealthy flight instructor. You'll learn them as you encounter them. Figure 10 shows the decoding of the METAR found in Figure 6. Automatic Weather Observing Programs. Automatic weather observing stations will soon serve as the nation's primary surface weather observing network. These weather-watching computers in a can transmit weather information, temperature, pressure, dew point, winds, cloud heights, etc., directly to you in flight. we'll discuss two types of automatic weather observing systems. Automatic Surface Observing System, ASOS, and Automatic Weather Observing System, AWOS. ASOS. ASOS is sort of a hyperactive AWOS. In addition to basic weather measurements, it also reports precipitation and intensity, as well as the occurrence of freezing rain. Situated at airports and other observing points nationwide, these automated stations provide minute-by-minute reports of the ever-changing weather. The intent is to establish 1,700 of these stations. One of the unique benefits of the automated system is that pilots can listen to computer-generated voice observations while airborne. Some computer voices sound like Darth Vader with a cold. These transmissions are usually receivable within 25 nautical miles of the airport and at below 10,000 feet HEL. Figure 11 shows an AFD excerpt for Wiscasset Airport, showing that ASOS observations can be heard on 135.725 MHz or heard by calling the listed phone number. ASOS reports are similar to the METAR that we've already studied. There are, however, a few subtle differences. Automated stations cannot, for instance, report clouds above 12,000 feet. However, the ASOS will report CLR, meaning no clouds are reported below 12,000 feet, instead of the SKC value as shown in the METAR. There could be a solid overcast at 15,000 feet, but the ASOS cannot identify it. Thus, it can't report it. Keep this little idiosyncrasy in mind whenever you see an observation annotated as auto, COR for corrected, or in the remarks you see AO1 or AO2. The AO1 or AO2 indicates the level of sophistication of the precipitation discrimination sensors associated with the ASOS unit. AO2, being more sophisticated, can discriminate between different types of precipitation, in other words, rain, snow, etc. Remember, if you see or hear of something missing from an ASOS report, it doesn't mean it's not there. It just means that the ASOS unit can't or didn't detect it. Figure 12 shows two ASOS weather observations. You can tell these are automatic type surface observations because the letters AUTO, meaning automated, and or COR are located directly after the location of the date and time identifier. As you can clearly see, the ASOS observations are provided in the same format as the METARs we've already studied. There's nothing new to be learned here. Simply read the ASOS observations like you do the METAR. See Figure 9 for a sampling of the codes for the remarks, RMK, found at the end of the ASOS or METAR observation. The ASOS observation for KABC shows auto, AUTO, right after the date-time group and the letters AO2 in the remarks section. This indicates that no human oversight backed up or augmented the ASOS report. Some locations have a human observer augment the ASOS report. Whenever the human observer augments or adds to the ASOS report, the auto is deleted, because now it is a manual observation. However, in the remarks section will still show either an AO1 or an AO2.
Personally, I am more inclined to place greater faith in automated weather reports when a human being oversees the process. That's why I don't trust those automated blood pressure machines found at shopping malls and airports. I heard of a pilot who put in his quarter, stuck in his arm,
and when his reading came up as 390 over 260, crikey, it wouldn't let him go like a crock until an FAA rep showed up. Just kidding. Tell us a joke. Remember, machines can't detect all weather.
AWOS. AWOS, Automatic Weather Observing System, are found at more and more airports across the country where weather reports were previously not available. Consisting of various sensors, a processor, a computer-generated voice system, and transmitter, these stations broadcast minute-by-minute, real-time, local weather information directly to pilots. AWOS and ASOS transmissions are receivable within 25 nautical miles of the transmission site, at or below 10,000 feet AGL. The transmissions can also be received on the airport. Frequencies for AWOS may be found near the airport data on the sectional chart, as shown in Figure 13, and in the AFD, as shown in Figure 14. 4 basic levels of AWOS stations are available. 1. AWOS-A reports only altimeter setting. 2. AWOS-1 usually reports altimeter setting, wind data, temperature, dew point, and density altitude. 3. AWOS-2 provides the information provided by AWOS-1 plus visibility. 4. AWOS-3 provides the information of AWOS-2 plus cloud ceiling data. A typical ASOS or AWOS voice transmitted observation might sound something like the following. Denver Front Range Airport. Automatic weather observation 1833 Zulu. Sky conditions 6,500 scattered. Visibility greater than 10. Temperature 22 Celsius. Dew point 19 Celsius. Wind 350 at 03. Altimeter 2978. Remarks: density altitude 7,500. Remember, just because it's a machine doesn't mean it won't make mistakes. The entire airport might be surrounded by clouds with a single solitary hole over the ASOS or AWOS-3 weather unit. You can bet that little puppy reports all clear. The entire airport may be shrouded in fog, while the ceilometer, cloud height measuring device, reports no clouds at the airport. Fortunately, the visibility would provide a clue to the presence of fog. When a human weather observer supplements mechanical weather observations, these problems disappear. Use a little common sense when using an automated observation of the weather on which to base your decisions. Wither the weather. Having the current weather for airports along your route is valuable, but this is just one bean short of a hill if you're planning tomorrow's flight. Weather changes from day to day, hour to hour, minute to minute. It also changes while en route. Pilots need a means of predicting this change. Since pilots don't have crystal balls, no matter what they may claim, most of them look into the future through more conventional means, such as one of several aviation forecasts which are available. Terminal Aerodrome Weather Forecasts, TAF. A terminal forecast sounds like it's the last weather you're ever going to get. Fortunately, this isn't what a TAF is all about. TAFs provide a description of surface weather expected to occur at an airport. They are an excellent means of identifying the weather you can expect upon arrival at an airport. You can compare forecasts for airports along your route to obtain a better idea of how the weather is expected to change. When used in conjunction with METARs, TAFs provide you with a good idea of the present weather and how it's expected to change. TAFs are forecast weather for a 24-hour period. They are issued 4 times daily, once every 6 hours. Much of the weather coding is similar to the METAR weather format. I knew that would make you happy. Since it's relatively simple to read, we won't need a memory-type acronym to interpret TAFs. If there are any major differences in the codes used by TAF compared to METAR, I'll let you know. Let's examine the TAF weather shown in Figure 15. Station KLAX. Same form and format as the METAR. Date forecast issued 091140Z. The report was issued on the 9th day, 09, at 11:40 Zulu, UTC. Time of forecast 091212. This forecast's date and valid times are indicated by the 6-digit number sequence 091212. The first 2 numbers represent the date, and the second 2 numbers represent the time the forecast period begins, 1200 Zulu. The last 2 numbers represent the ending time of the forecast period, 1200 Zulu. The forecast is valid from 1200 Zulu on the 9th to 1200 Zulu on the 10th, a 24-hour period. If midnight UTC is the beginning time period of the forecast, it will be coded as 00. If it is the ending time, it is coded as 24. Therefore, a 24-hour forecast beginning and ending at midnight UTC would be indicated as 0024. Forecast winds 22020 KT. This is presented in the same format as the METAR. Figure 15 shows winds forecast to be from 220 degrees true direction at 20 knots. Winds will always be indicated regardless of their velocity. Forecast visibility 3SM. This is the prevailing visibility expected in statute miles up to and including 6 miles. Expected visibilities greater than 6 miles are forecast as P6SM plus 6 statute miles. Forecast weather minus SHRA. The same 5 categories used in a METAR are used in a TAF for reporting weather phenomena, as shown in Figure 8. The letters minus SHRA represent only operationally significant weather that's forecast for the implied time period. In other words, light rain showers are forecast starting at 1200 Zulu. Forecast cloud conditions BKN020. This is the same as the METAR format. In this example, broken clouds are forecast at 2000 feet AGL. As in the METAR, ceiling layers are designated by the lowest layer, that's BKN, broken, OVC, overcast, or shows VV, vertical visibility, into an obscuration. Expected changes BECMG, FM, TEMPO, PROB. When gradual changes in the prevailing conditions are expected, usually over a period not to exceed 2 hours, the abbreviations BECMG, becoming, is used. BECMG is followed by 4 digits. The first 2 digits indicate when the change is expected to begin, and the last 2 digits indicate when it's expected to be completed. The weather conditions that follow are expected to change at a gradual rate over the depicted time period. Any weather condition forecast prior to BECMG, which is not revised following the change time period, is expected to remain the same. For example, our report showing 1619 after BECMG means that from 1600 Zulu to 1900 Zulu, the wind is expected to change to 330 degrees at 15 knots, and all other weather is expected to remain the same. FM is followed by a 4-digit number, which indicates the beginning time of a self-contained portion of the forecast. This is used when a rapid or significant change in weather, usually occurring in less than 1 hour, is expected. In our report, the sequence of FM 0300 indicates that from 0300 Zulu, the following weather conditions should occur: winds 350 degrees at 14 knots, 2 miles visibility, thunderstorms and rain, and an overcast ceiling of 1,500 feet. Weather that's omitted in the FM group isn't significant to aviation. TEMPO indicates that fluctuations, temporary and usually lasting less than 1 hour, from the predominant weather conditions are expected. TEMPO is followed by a 4-digit number, 0612, indicating the time period that these variations are expected. In our report, a temporary condition of 1 mile visibility and heavy rain is expected to occur between 0600 Zulu and 1200 Zulu. PROB, probability, is used when the likely occurrence of any weather phenomena falls in the 30 to 39% probability 30, or 40 to 49% probability 40 range of expectation. If the probability of the condition is 50% or higher, the terms BECMG, TEMPO, or FM will be used. In our report, the sequence PROB40 0809 1/2SM FG indicates that between the hours of 0800 Zulu and 0900 Zulu, there is a 40 to 49% probability of 1/2 mile visibility in fog. Figure 16 shows a detailed analysis of an airport's TAF.
Remember, terminal aerodrome forecasts are issued once every 6 hours. Make it a point to check the latest TAF for the most current forecast information. I make it a point to check the METAR against the TAF. If the TAF said this hour was to be clear, but the METAR showed clouds, then that particular TAF might be too optimistic. I might then be less inclined to place a great deal of trust in its accuracy. Once something isn't right, you're disinclined to trust it. That's why I never trusted my uncle's communication skills. When I was young, he told our neighbor to drop me off at the nursery on our way back to work. For an entire day I sat, surrounded by plants and trees.
Area Forecasts, FA. Remember the anxiety you felt when you went to a drive-in theater and drove off without unhooking the speaker? 5 blocks away you heard, "Attention, attention, the snack bar will be closing in 15 minutes. Okay, perhaps this never happened to you, but you might feel a similar sensation when looking at the area forecast. It consists of a lot of words without vowels. This is part of the carryover from those days when teletypes were slow and words were abbreviated to speed things up. With just a little practice, You'll be interpreting these reports as fast as Einstein whipping through nonlinear differential equations. The Area Forecast, FA, is a general forecast often covering a region that includes several states. It's your key to finding the expected weather en route and at airports not having terminal aerodrome forecasts. Not every airport has a terminal aerodrome forecast, which makes the area forecast your only forecasting tool. Figure 17 shows a typical area forecast. FAs are issued 3 times daily for 6 specific areas in the lower 48 United States. They are 12-hour forecasts with an additional 6-hour outlook. As with other weather reports and forecasts, times are in Zulu. Unlike the terminal aerodrome forecast, however, the area forecast presents its cloud heights in MSL rather than AGL, unless noted by an AGL or ceiling designation. This is logical once you think it through, since the forecast isn't for a specific spot, but rather a huge area over which there is often considerable variation in terrain height. In the area forecast, a ceiling is identified by CIG, which means ceiling. Figures 18a and 18b show a few of the common contractions, definitions, and variability terms used in the FA and other weather reports and forecasts. The FA consists of 4 sections. 1. Communications and Headers section. 2. Precautionary Statements section. 3. Synopsis section. 4. VFR Clouds and Weather section. Let's examine the FA in Figure 17. The first section of the FA was issued for the Salt Lake City area. The C, following SLC, indicates that this forecast contains clouds and weather. This forecast was issued on the 26th day of the month, 26, at 10:45 Zulu. Underneath this line is Synopsis and VFR CLDS /WX, which tells you what's in this forecast in case you don't already know. The next line states that the synopsis is valid until 0500 Zulu on the 27th day of the month, 270500. The line underneath indicates the CLDS/WX section is valid until 2300 Zulu on the 26th, a 12-hour period from the time the forecast begins. Note that the synopsis is valid for 18 hours, while the VFR Clouds and Weather section is valid for only 12 hours. The OTLK, or Outlook information, is valid from 2300 Zulu on the 26th to 0500 Zulu on the 27th. That's a 6-hour period. Following this are the states making up the forecast area. Idaho, Montana, Wyoming, Nevada, Utah, Colorado, Arizona, and New Mexico are covered in this area forecast, as shown in Figure 19.
As you can plainly see, vowels are left out of the report where possible to condense it for transmission. Don't try to speak without vowels, unless you enjoy sounding like a Klingon. Fortunately, weather briefers read it to you in real English. That's because Klingons don't get weather briefings. They go regardless of the weather. It's not, however, difficult to read once you've had a little practice, since there are only 5 vowels, A, E, I, O, U! For those of you long out of school, you can always substitute until you get something that sounds like an English word.
The precautionary statements sections in Figure 17 is next. These statements are included in all area forecasts. Any IFR conditions or mountain obscuration that are present or expected to occur will be covered in something called an AIRMET, AIRMET, Air Meteorological Advisory. As you'll soon see, these are advisories of significant weather phenomena and should be of concern to you. Keep in mind that hazardous weather, IFR, icing, and turbulence are not included in the area forecast. You must refer to AIRMETs and other in-flight aviation weather advisories for this information. We'll discuss these shortly. The next statement indicates that thunderstorms imply possible severe or greater turbulence, severe icing, and low-level wind shear and IFR conditions. The last statement indicates that all heights in the area forecast are MSL unless otherwise noted. The synopsis section of the area forecast is simply the big picture of what's going on. It is a brief summary of the location and movements of fronts, pressure systems, and circulation systems for an 18-hour period. Figure 20 shows how you might mentally picture this synopsis. The VFR Clouds and Weather section contains a 12-hour specific forecast, followed by a 6-hour categorical outlook. This gives us a total forecast period of 18 hours. You'll find the VFR Clouds and Weather, or VFR CLDS/WX section, several paragraphs long. It's often broken down by states or by well-known geographical areas. A general description of clouds and weather which cover an area greater than 3,000 square miles and is significant to VFR flight operations follows each of the listed geographical areas. In order to interpret the area forecast, it's best to start with the synopsis section. Personally, I like this section best. Why? Because it's frank and to the point. I guess you could say that this is the place to get a frank synopsis. He was a great guy, wasn't he? According to the synopsis shown in Figure 20, a cold front, CDFNT, extends, EXTDS, from eastern, ERN, Montana across, ACRS, southwestern, SWRN, Montana, and southwestern Idaho into northwestern, NWRN, Nevada, into northern, NRN, California. By 0500 Zulu, the end of the outlook's valid time, the cold front will extend from northwestern Minnesota and eastern South Dakota across central, CNTRL, Nebraska, and southeastern, SERN, Idaho, into northwestern Nevada and northern California. An upper-level UPRLVL, low-pressure system, SYS, over OVR, northern New Mexico will move slowly, SLOLY, southward, SWD, during DURG, this period, PD. Once you've looked over the synopsis, forecast weather for individual states or specific locations in the VFR CLDS/WX section will make more sense to you. Figure 21 provides an interpretation for Idaho's weather. Keep in mind that surface visibility and obstructions to vision are only included in the area forecast when the forecast visibility is expected to be 6 statute miles or less. Precipitation, thunderstorms, and sustained winds of 20 knots or greater are always included when forecast. Winds aloft forecasts, FD.
Well, boys, I reckon this is it. There are certain moments in your life you just don't forget. A fellow once came up and said he was going to punch my nose in. I said, "Hey, don't you know that you never end a sentence with a preposition?" At that point, he proceeded to punch in my nose. Some folks are pretty tough, but no matter how tough you are as a pilot, you're never going to win a fight with the wind.
The way to keep from being beat, however, is to know how fast and from what direction the wind blows. This is extremely important for planning proper fuel consumption, not to mention figuring out whether you'll be getting to your meeting on time. Fortunately, there is a forecast that provides you with an estimate of winds for up to 24 hours in advance. It's known as the Winds Aloft Forecast. Winds aloft forecasts are very useful to pilots. These forecasts are issued twice daily and are valid for either 6, 12, or 24 hours. Each forecast is issued with a valid time for its use. Figure 22 shows a typical winds aloft forecast. Winds are forecast for true altitude starting at 3,000 feet and additional 3,000-foot increments up to 12,000 feet. We won't worry about higher altitudes for the moment. Winds less than 1,500 feet above the reporting station's surface are not forecast. In other words, if your airport lies at 5,000 feet MSL, the 6,000-foot winds aloft forecast will be blank for the area around the airport. Temperature is not forecast for altitudes within 3,000 feet of the surface. Winds aloft are provided in knots, and their direction is always in reference to true north, as are other weather reports and forecasts. Figure 22 depicts the forecast winds at 6,000 feet MSL above AMA, Amarillo, Texas, as 2714. Unlike METAR or TAF, the first two numbers of this four-digit value represent the wind direction in tenths of degrees. You need to add a 0 onto these numbers to get the wind direction. The last two numbers represent the wind's velocity. The wind at AMA is forecast to be from 270 degrees at 14 knots. At 6,000 feet MSL above MKC, the wind is forecast to be from 200 degrees at 6 knots, with a forecast temperature of +3 degrees C. The minus or plus after the winds represents a negative or positive temperature value which follows the four-digit wind value. Winds aloft temperatures are in degrees Celsius. At 9,000 feet MSL over DEN, Denver, Colorado, the winds are forecast to be from 230 degrees at 21 knots, with a temperature of -4 degrees C. If winds are expected to be light and variable, the identifier 9900 is used. This doesn't mean wind from 990 degrees with no velocity. We can't have a wind with an unknown direction and no speed. Technically, it means that the winds are less than 5 knots. Calm winds are identified by 0000. Forecast temperatures are useful for several reasons. Many pilots use them to predict where temperature inversions will be. Anytime you see the forecast temperature increasing, or not decreasing as much with altitude, you know you have a stable air situation. Warmer air aloft could act as a lid, trapping industrial pollutants. If you want the winds at an altitude between those listed, it's time to interpolate, also known as meeting the numbers halfway. Break out the crazed supercomputer. Actually, the math is easy, and you can probably do it either in your head or on your fingers. If the altitude you'll be flying at is halfway between two forecast levels, the wind and temperature will be about halfway between the numbers given for those two levels. Add the two wind or temperature numbers together and divide by 2. Bingo! I told you it wasn't calculus. Actually, Halfway is about all you'll ever need to figure. If you're closer than that to one forecast level or another, use it and you'll be close enough for rock and roll. If you believe there is a significant difference between the winds at 6,000 feet and the winds at 6,750 feet, and that this can be forecast with great precision, then please call me about some low-lying land I have available in Florida. One of the most important items to check during cross-country flight planning is the altitude which will provide the most favorable, or at least the least adverse, winds. After studying the winds aloft forecast, you can easily decide on an altitude giving you less of a headwind or more of a tailwind. Sometimes it's advantageous to spend additional time climbing in order to catch a tailwind. Weather charts. Getting the big picture. Okay, you don't like numbers and you're not real big on words. You bought this book and that copy of Play Pilot you're holding for the pictures. Fortunately, when it comes to weather, you haven't been left out in the cold. Much of the complexity of weather makes a lot more sense presented as pictures, which is the way weather people have been looking at the weather for decades. Even if you can't picture yourself reading charts, join me for a few moments and take a look at what you're missing. There are a number of weather charts that can prove most informative. Accessing them was easy when there was a flight service station on almost every airport corner. If you have a personal computer, the charts are now available from a variety of sources electronically and in color, so you can brief yourself from the comfort of your home. And if you are fortunate enough to be near one of the remaining flight service stations, stop in and look at some of the following charts. It's a great way to literally get the picture. Weather Depiction Chart. The Weather Depiction Chart, Figure 23, is prepared from METARs. It provides pilots with a broad overview, a bird's eye view in other words, of weather conditions. It's an excellent place to begin your briefing and determine the general weather conditions upon which to base your flight planning. The chart is issued every 3 hours, beginning at 0100 Zulu. The Weather Depiction Chart has lots of good information. Perhaps most important is the graphic view it gives you of where VFR and IFR conditions prevail. The Weather Depiction Chart always comes with a means of decoding a few of its symbols. A decoding key is located in the bottom right-hand corner of the chart. For instance, any area that is shaded is IFR, ceilings less than 1,000 feet and or visibility less than 3 miles, position A. Contoured areas without shading are areas of marginal VFR, MVFR, weather, with ceilings greater than or equal to 1,000 feet to less than or equal to 3,000 feet and or visibility of 3 to 5 miles, position B. Areas without contours are areas of VFR with ceilings greater than 3,000 feet and visibilities greater than 5 miles, position C. Numbers and symbols surrounding the individual stations inform you about clouds, heights, coverage and weather, and obstruction to vision. A key for this chart symbol is shown in figures 24 and 25. Note: only the code shown on the actual weather depiction chart is provided to you on the knowledge exam. For instance, in the southeast corner of New Mexico, position D, the station circle is completely darkened in. Using the key in figure 24, you can tell that the sky is overcast. Cloud height is determined the same way it is with the METAR and TAF, by adding 2 zeros to the numbers underneath the station circle as shown in figure 25. This tells us that the height of the overcast with the numbers 60 under the station circle is 6,000 feet, Visibility and precipitation is shown to the left of the station circle. Our station has a visibility of 4 miles with thunderstorms, and rain showers indicated by the small black dot on top of the thunderstorm symbol.
Another nice thing about the weather depiction chart is that it shows the location of frontal systems using symbols similar to those on the surface weather map. Before your detailed flight planning begins, take a look at the weather depiction chart. Ask yourself these questions. Are there VFR or marginal VFR conditions in the direction I'm headed? Which way is the front moving? Which is more important, existence or essence? Oops, sorry, that's an optional question. The weather is sure to become worse in the direction of frontal travel.
Well, let's see now. The great value of the weather depiction chart lies in its frequency of issuance. You only get that advantage, however, if you're using the latest product, just as you look on a box of cookies for the expiration date, don't you? Check when the weather depiction chart was issued. If it's stale, get another one, punk.
Radar Summary Chart. The radar summary chart, shown in Figure 26, is issued 16 times a day during a 24-hour period. Some private weather services offer it 24 hours a day. It presents the location of radar echoes resulting from precipitation, usually water or hail, suspended in clouds. Since radar energy is incapable of reflecting off clouds, this chart does not directly show cloud locations, though you can surmise that where there's rain, there are clouds. The absence of a radar return, however, doesn't mean that there are no clouds. Radar energy goes right through a cloud. It takes precipitation-size water drops to show up on radar in the form of a precipitation echo. If enough suspended water is present, the radar will show its location. Keep in mind that it also takes updrafts to suspend water, and strong updrafts are associated with thunderstorms. If the radar shows enough water, there's a strong possibility thunderstorms are present. By examining the radar summary chart, you'll be able to determine the location of precipitation echoes, their intensity, intensity trend, configuration, coverage, echo tops, bases, and movement. While this chart is primarily of value to the instrument pilot, it can also provide the VFR pilot with much useful information. Figure 27 provides you with a legend to interpret the symbols on the radar summary chart. This won't be available on the knowledge exam, so there are a few items you'll need to memorize. On the east coast of Florida, near Area C, there is a single, non-feathered arrow pointing northeast with the numbers 05 near its tip. A single arrow represents an individual cell movement in the direction specified with a speed, in this instance 5 knots. The RW+ indicates rain showers with increasing intensity. On radar summary charts, a plus or minus sign after the precipitation indicates the intensity trend of that precipitation. The tops of the echoes are 26,000 feet. Remember, this is the tops of the precipitation inside the cloud, not the cloud itself. Area A indicates radar echoes moving east at 15 knots. The arrow has feathers, meaning that it's a line or area movement instead of just a cell, an arrow without any tail feathers. The arrow near A has 1.5 feathers. Each feather represents 10 knots of speed. That's how you arrive at the conclusion that radar echo movement is easterly at 15 knots. In Area D, the radar return is moving northeast at 20 knots. Since it's a single arrow without feathers, this represents the movement of an individual cell. The highest top of the precipitation around Area D is 30,000 feet, indicated by the 300 with an underline pointing to an area of echoes. Whenever a severe weather watch is in effect, the affected area is surrounded by a dashed line as shown in Area B. A severe weather watch area can include tornadoes or severe thunderstorms, neither of which is an invitation to fly by in a small aeroplane. And believe me, when it comes to this kind of weather, any kind of aeroplane is small. As a VFR pilot, the radar summary chart is helpful because it provides clues on where the air is convectively active or the weather is severe. The greater the suspended precipitation, the greater the intensity of the updrafts required to suspend it. When you have echoes with 3 contours indicating intense or extreme echo intensity, then you have a greater chance of extreme turbulence and its associated problems. The taller a thunderstorm, the nastier it generally is. Precipitation heights provide you with a rough idea of just how strong the echo or the areas of echoes is.
An additional source of information comes from the speed of the cells or areas of echoes. Faster moving echoes or cells are generally nastier. They usually contain more turbulence, precipitation, wind shear, etc. Observe arrow feathers that indicate cell or echo speed. Combine this with an observation of the height of a radar return. Shake gently, think carefully, and plan ahead. Consider whether you should go at all. If you do go, have a backup plan in case you can't comfortably reach your destination. That means having spare fuel on board. Now, I don't know much about anything. I don't remember my first birthday or my first outdoor picnic. But I do remember what Mark Twain's mama once said. She said that it's better to be cautious 100 times than to die once.
Low-level significant weather prognostic chart. A doctor told his patient that he had good news and bad news. The doctor asked which the patient wanted to hear first. The patient said, "Give me the good news first." The doctor said, "Well, you've got 24 hours to live." The patient said, "That's the good news? What's the bad news?" The doctor said, "I tried to call you yesterday." Essentially, the doctor gave his patient a prognosis, or a future outlook. While the terminal area forecast, and winds aloft forecast are all a textual prognosis of the weather, the low-level significant weather prognostic chart does the same thing in picture form. The low-level significant weather prognostic chart, the prog chart, as it's usually referred to by those not wishing to carry supplemental oxygen, is a graphic version of the area forecast, though it differs slightly from the written version as shown in Figure 28. While the area forecast provides weather for one of 6 forecast areas in the United States, the prog chart provides a picture forecast for the entire U.S. The prog chart consists of 4 panels. The upper panels are 12-hour left panel A and 24-hour right panel B prognoses of significant weather from the surface to the 400 millibar pressure level. That's 24,000 feet. The lower panels, panels C and D, are 12 and 24-hour prognoses of surface weather. Prog charts are issued 4 times daily, approximately once every 6 hours. A key located between both upper charts helps with interpreting the weather symbols. For instance, all areas surrounded by solid lines are areas with ceilings less than 1,000 feet and/or visibility less than 3 miles. These are IFR conditions, and the code is similar to that used on the weather depiction chart. Areas surrounded by scalloped lines are marginal VFR conditions consisting of 1,000 to 3,000 foot ceilings and or 3 to 5 miles visibility. Areas outside scalloped lines are forecast to have ceilings greater than 3,000 feet and 5 miles visibility. Panels A and B of the significant weather prog chart have zigzag lines which indicate the location of the freezing level at the surface. Panel A, position 1. Dashed lines on the same panel indicate freezing levels at altitude. Panel A, position 1. Freezing levels are important for instrument pilots, since they want to avoid flying in the clouds when the temperatures are near or below freezing, lest they pick up ice on the plane and turn their aircraft into a giant snow cone. An additional and very useful feature of the significant weather prog chart is its forecast of turbulence. The long dashed line surrounding California, Arizona, and parts of New Mexico and Colorado indicates moderate or greater turbulence is forecast during the 12-hour time period. Panel A, position 2. Use the key between the panels on the prog chart. Within the area surrounded by the long dashed line is the number 180 on what appears to be a witch's hat symbol above it and a small, short diagonal line to the right. The 180 means this turbulence is forecast from the surface up to 18,000 feet. In the 24-hour significant weather prog, panel B, position 3, the 080 indicates that moderate turbulence is forecast for this area from the surface to 8,000 feet during the forecast time. A number to the right of the diagonal line, in other words, the stroke or slash to the right of 080, indicates the base of the turbulence when it doesn't begin at the surface. By comparing the 12 and 24-hour significant weather prog, you can visualize the direction of weather movement during the next 24 hours. Figure 29 and 30 show additional symbols used in this chart. These figures aren't provided on the private pilot knowledge exam. The 12 and 24-hour surface prog, panels C and D, provides you with the expected location and movements of fronts, pressure systems, and their generated weather. The 12-hour surface prog, panel C, forecasts a low-pressure center over northern Utah, panel C, position 4. The unshaded area within the solid line that circles several western and northwestern states indicates that the forecast precipitation will cover half or less of this area. The symbol ** /lowercase star uppercase star lowercase star and its arrow pointing to the shaded area of the Utah low indicates continuous and moderate snow is forecast. Use the key in Figure 30 to help with this interpretation. By comparing panels C and D, you can see that the low is forecast to move northeastward into Wyoming. According to Figure 29, the shaded area surrounding the low indicates that the continuous snow, the precipitation, is still expected to cover more than half of the area during the latter part of the forecast period. In the 24-hour surface prog chart, the west coast of Florida is expected to have continuous and moderate rain, 3 dots, and slight or moderate thunderstorms with rain indicated by the thunderstorm symbol, with a single dot above, panel D, position 5. I think a good thunderstorm symbol is a tiny picture of a pilot's face with his eyes bugging out and a Don King hairdo. The area in the upper part of North Carolina, Panel D, Position 6, is expected to have continuous slight rain showers. 2 dots indicates continuous rain, and the dot above a triangle indicates slight rain showers. According to Figure 29, since the entire area is enclosed by a solid line, the precipitation is expected to cover less than half of the area. By comparing panels C and D, it appears that the poor weather on Florida's western coast will move eastward. Panels A and B, however, suggest that all of Florida will still have ceilings of 1,000 to 3,000 feet and/or visibilities of 3 to 5 miles. Surface analysis. The surface analysis chart, Figure 31, shows the location of pressure patterns and fronts. This chart is based on reported weather data and is issued every 3 hours. Individual reporting stations and their associated weather are depicted on the chart. Additional decoding information for the station model on this chart can be found in the FAA's Aviation Weather Services Manual, AC 00-45D. Even without a detailed understanding of this chart's symbology, you can derive some interesting information from it. Think of the surface analysis as a very large visual portrayal of hundreds of METARs, surface weather reports. Although this chart's information may be older than that of the individual METARs, it can provide you with a big picture of the weather for individual stations along your route. For instance, the chart shows the temperature dew point spread over a large area. From this, you can get a good feel for the likelihood of fog or low cloud formation before and after sunset. Orientation of the isobars and the pressure patterns gives you an idea of surface winds. Cloud coverage at the time the chart was constructed is identified by the fill on the individual station circles. In addition, you can determine the types of clouds existing en route. Much more useful weather material exists on the surface analysis chart. Personally, I like comparing the present location of pressure systems and fronts using the surface analysis with the predicted future locations on the 12 and 24-hour prog chart. This tells me where these fronts are now and where they're likely to be in the future.
Hey, you know what I think? I think this is being similar to the actions of professional boxers who want to know where their opponent is and where they might move. Personally, I've always thought of boxing as being similar to ballet, except there are no leotards, no music, and the dancers get to hit each other.
In-flight aviation weather advisories. Most people want to protect things that are of value to them. For instance, my parents used to have plastic covers on their living room furniture to protect it. My grandfather was different. He tried to make visitors wear plastic leisure suits instead of opting for covers. It didn't work too well, but our guests did lose weight. Pilots want to protect themselves while airborne. They do so by understanding what in-flight advisories are and how they're disseminated. In-flight aviation weather advisories are forecasts which advise pilots of potentially hazardous weather, some of which might have been forecast and some of which might have arrived as a complete surprise to everyone involved. These advisories are provided to the flight service station and are normally included in your standard weather briefing. Always make it a point to ask the briefer for any in-flight advisories anyway. In-flight advisories may also be obtained during TWEB and HIWAS broadcasts over specific VORs and NDBs. EFAS, Flight Watch, also has the full listing of in-flight advisories, so you may easily access them in flight via a radio call. There are three types of advisories: convective sigmets, and eremits. Sigmet, WS. A sigmet is an advisory of non-convective weather, non-thunderstorm type activity that is potentially hazardous to all aircraft, big and small. Sigmets are issued when any of the following occur or are expected to occur: severe icing not associated with thunderstorms, severe or extreme turbulence or clear air turbulence, CAT, not associated with thunderstorms, dust storms, sandstorms, and volcanic ash that lowers surface visibilities to less than 3 miles, and, finally, any volcanic eruption, something we pilots are not trained to handle and don't want to see while it's occurring. Any of these items certainly affects both large and small aeroplanes. Sigmets are named by the phonetic alphabet, using designators from November through Yankee, excluding Sierra, Tango, and Zulu. These three are eremit designators. By knowing the specific phonetic name and number of a sigmet or eremit, you can call the Flight Service Station, or EFAS, and determine if it has been cancelled, continued, amended, or updated. Figure 32A shows a typical sigmet and the area it affects. This sigmet was issued for the DFW area at 1710 Zulu on the 5th day of the month and is valid until 2110 Zulu on the same day. The letters UWS, Urgent Weather Sigmet, are included in the first issuance of a sigmet. Sigmets have names for identification. This sigmet is named Papa 1, indicating that this is the first sigmet issued in that specific area. Issuances for the same weather phenomena will be sequentially numbered using the original name, Papa 2, Papa 3, etc., until the phenomena ends. The sigmet in Figure 32A is for Arkansas, Louisiana, and Mississippi. From MEM to 30 miles north of MEI to BTR to MLU to MEM, you can expect occasional severe icing above the freezing level. Remember, these three-letter identifiers are all VORs in the affected area. The freezing level is from 8,000 feet eastward to 12,000 feet westward, conditions continuing beyond 2100 Zulu. 4 hours is the maximum forecast period of a sigmet. Eremit, WA. Eremits warn of significant weather but describe conditions at intensities lower than those which trigger sigmets. They are intended for all pilots in the pre-flight and en route phase of flight to enhance safety. Eremits are issued once every 6 hours on a scheduled basis, with unscheduled amendments issued as required. Each eremit issuance contains current eremits still in effect, significant conditions not meeting eremit criteria, and an outlook for conditions expected after the eremit valid period. Eremits are valid for a period of 6 hours. They contain one or more of the following weather phenomena when they occur or are forecast to occur: moderate icing, moderate turbulence, sustained winds of 30 knots or more at the surface, ceilings less than 1,000 feet and/or visibilities less than 3 miles, affecting over 50% of the area at one time, as well as extensive mountain obscuration. The upper portion of Figure 32B shows an eremit and the area it affects. It was issued for the Dallas-Fort Worth forecasting area on the 5th day of the month at 1445 Zulu. The T following DFW indicates the type of eremit. In this instance, it means Tango for turbulence. Aramet Tango is updated and is valid until 2100 Zulu on the 5th day of the month and applies to the area around Tennessee, Alabama, and the coastal waters. The area described in the Aramet is expected to have moderate turbulence below 6,000 feet MSL due to strong and gusty low-level winds. These conditions are expected to continue beyond the Aramet's valid time of 2100 Zulu. Aramet Sierra in the lower portion of Figure 32 is on its third update. The S following DFW indicates Aramet Sierra, which indicates IFR conditions or mountain obscuration. The bordered area shown is expected to have occasional ceilings below 1,000 feet and visibilities below 3 miles in precipitation and fog. Conditions are expected to continue beyond 2100 Zulu through 0300 Zulu. If you're planning on doing any traveling to this area during the forecast time, you might think about doing it by car. Aramets have fixed alphanumeric designators. If you see Aramet Sierra, this stands for IFR and mountain obscurations. Tango stands for turbulence, strong surface wind, and low-level wind shear. And Zulu stands for icing and freezing level. Do you recall the precautionary statements section in the area forecast? It's said to see Aramet Sierra for IFR conditions and mountain obscuration. This is why you always need to check for airmets that may affect your flight. Convective sigmets, WST. Another version of the sigmet is the convective sigmet, WST. They are the granddaddy of in-flight advisories and present hazards to all aircraft. A convective sigmet is an advisory associated with convective activity such as severe thunderstorms. Any convective sigmet implies severe or greater turbulence, severe icing, and low-level wind shear. A convective sigmet may be issued for any of the following items. 1. Severe thunderstorms due to A. Surface winds 50 knots or greater. B. Hail at the surface greater than or equal to 3/4 inches in diameter. C. Tornadoes. 2. Embedded thunderstorms. 3. A line of thunderstorms. 4. Thunderstorms greater than or equal to VIP level 4, affecting 40% or more of an area of at least 3,000 square miles. Figure 33 is an example of a convective sigmet. This sigmet was issued on the 22nd day of the month at 1855 Zulu. It is the 20th consecutive sigmet, 20C, issued on this day in the central U.S. The sigmet references a line in the vicinity of GLD to CDS. It forecasts a line of thunderstorms developing by 1955 Zulu and moving eastward at 30 to 35 knots through 2055 Zulu. Hail to 1 1/2 inch is also possible. That's pretty serious weather. You better be on the ground wearing a hard hat and a roll bar if you experience hail that size. Convective sigmets also contain an outlook. This is a forecast for thunderstorms that are expected to require convective sigmet issuance during a time period 2 to 6 hours into the future. The convective sigmet outlook in Figure 33 indicates isolated strong thunderstorms will develop over southwestern Kansas through the forecast period as an upper-level trough moves northeastward over very unstable air. Pilot reports, PIREPS, PIREPS. Pilot reports provide pilots with some of the best real-time weather information available. PIREPS provide an excellent means of finding current weather between reporting stations. Flight Service Station and Flight Watch, as well as other ATC specialists, long for pilots to give reports of weather and other items of interest, particularly any unforecast conditions you might encounter. Pilot reports don't have to relate to weather information only. Reports of flocks of birds, balloons, and other items affecting flight are helpful. I remember seeing the following pilot report distributed by a Midwest flight service station, decoded for your convenience. Pilotless aeroplane, Aronka Champ, last seen heading northeast of Goodland at 3,000 feet. It seems the aeroplane was being hand-propped without a qualified pilot aboard. The engine started, and with the throttle set too high, the aeroplane zoomed off through a field and became airborne, after narrowly giving the pilot a crew cut. It remained airborne for a little over an hour before slamming into a farmer's field. Shouldn't this be called a non-pilot report or a no pilot aboard report? Pilot reports are officially coded, then disseminated through the ATC system for use in flight planning. The official format for this coding is shown in Figure 34A. Figure 34B shows how PIREPs are encoded. Let's examine a few reports. Figure 35 shows a typical pilot report. It reads, a routine PIREP. UA means routine. It doesn't mean United Airlines either. UUA means urgent. From Oklahoma City to Tulsa at 1800 Zulu at 12,000 feet. FL means flight level and is used for any altitude. Reported by a Beech 90. The type of aircraft is important. If a 747 reported light turbulence, it could mean moderate or severe turbulence for a small airplane. The base of the first cloud layer is at 1,800 feet MSL, broken with tops at 5,500 feet MSL. Since a pilot reported this, he or she is referencing the altimeter, which displays height in MSL values. This means, for example, that if the ground elevation is 1,295 feet MSL, then the 1,800-foot MSL ceiling is 505 feet above ground. The base of the second overcast cloud layer is at 7,200 feet MSL, and tops are at 8,900 feet MSL. And the weather is clear above the upper layer. Weather type, flight visibility is 3 miles in moderate rain. Temperature is -9 degrees Celsius. The wind is from 080 degrees at 21 knots. Pilots can determine wind direction and velocity from the cockpit by using sophisticated GPS and Loran systems. Turbulence is light, between 5,500 feet and 7,200 feet. There was light to moderate rime icing between 7,200 feet and 8,900 feet. Pilot reports are quite useful. They are, however, most meaningful when they are first issued. Conditions can change with time. Be very suspicious of pilot reports more than an hour old. Putting it all together. The secret to successful flight planning is in anticipating the weather's behavior. Comparing one chart or forecast to another greatly enhances this understanding. Here's one way of making these comparisons. There are other ways too. Surface map and weather depiction chart. Looking at the surface weather map tells you where the fronts and pressure systems are. Comparing this with the weather depiction chart provides you with a picture of what effect these fronts and pressure centers are having on surface weather. Figure 36 shows a typical comparison. weather depiction chart, and radar summary chart. With this comparison, shown in Figure 37, you can get an idea of the convective activity associated with areas of IFR, MVFR, and VFR conditions. If an area of MVFR conditions is associated with large, fast-moving echoes, meaning thunderstorms, you might want to reconsider planning a flight in this direction. Thunderstorms mean turbulence and rain showers. Couple this with ceilings of 1,000 to 3,000 feet and visibilities of 3 to 5 miles, and you might be pushing your VFR flying luck. Keep in mind that the weather depiction chart will generally be a few hours older than the radar summary chart. Area forecast and prog charts. Since the area forecast is a text-based description and the prog chart is a picture, comparison provides you with a complete, big-picture description of forecast weather. Figure 38. Weather depiction and prog charts. Since the weather depiction chart shows the location of fronts and pressure systems, you can see which way these systems will move by comparing them against the 12 and 24 surface prog chart, as shown in Figure 39. You also get an idea about what kind of weather IFR, MVFR, VFR will develop along the front by referring to the prog chart. METAR's surface map. Compare individual METARs with the surface weather map as shown in Figure 40. This provides you with an understanding of surface weather around and between your departure and destination airports. If the surface weather map reporting stations are all darkened in along your route, this means you might be flying above a layer of clouds even though the destination airport is reporting clear conditions. Look at the isobars and, using your knowledge about clockwise and counterclockwise airflow around highs and lows, decide on a route that increases the likelihood of a tailwind. Remember, the surface weather map information can be up to 3 hours old. Finally, examine the winds aloft forecast for temperatures and the selection of a favorable cruising altitude. Then examine the convective sigmets for thunderstorms, sigmets for any severe conditions, and any airmets for IFR conditions, turbulence, or pertinent icing conditions as shown in Figure 41. Sunny side up. A pilot's skill at handling weather is based on his or her weather sense. In other words, pilots must continually educate themselves about how weather works. Unfortunately, some pilots don't do this. I have a friend who is so weather insensitive, he probably couldn't even tell you when it's sunny or rainy. This presents a special problem for him since he is always forgetting where he left his sunglasses. It's not unusual for him to leave his glasses parked on top of his head. One of these days, he's going to have 3 or 4 pair up there, walk out into the sun, and start a little fire on his toupee. Make it a point to check the weather every day, even if you're not flying. Call the flight service station or patois, look at the newspaper weather chart, check your personal computer if you use Duat, JetBlink, or other service, or take a look outside and compare it to what happened yesterday. This is how pilots develop a weather sense. It's a sense that will offer you many years of safe flying. Post-flight briefing number 13-2. The Internet. More weather than you can imagine. The following statement summarized my experience with surfing. The closer you get to the beach, the shorter the sentences become. Hang 10 and hang on. That was until I discovered an entirely different type of surfing, called surfing the net. Of course, I mean Internet, the network of worldwide interconnected computer systems that talk with one another. Surfing the net has nothing to do with whales, water, or wharves. It involves using your computer, its modem, and the necessary software, a web browser, to browse the information stored in these interconnected computers. Of course, you only have access to information others want you to see, and there's a lot to see. In fact, the Internet is a wonderful place to learn about weather, as well as collect weather information for your flight. The web, or World Wide Web, is the graphical interface portion of the net, for those folks who like to see what they're doing. Links of interconnected computers from universities, colleges, government sites, and commercial companies from around the world are all available for you to access with your web browser. AOPA's weather and flight planning page sites are excellent. Figure 46. These are members-only locations, but this is simply another good reason to become an AOPA member. Another site called the Weather Information Superhighway also contains a comprehensive collection of meteorological data, information, and image sites from around the globe. You can find it at http://wxhw.noaa.gov/tlh/wxhwy.html. Once you log on, you'll have access to a large assortment of current weather charts. These include surface progs, weather depiction charts, radar summary charts, surface analysis charts, and much more. The following are just a few of the charts available from the NWS website. Two other websites offering excellent weather information are at Landings, Intellicast, and Weather. Landings' website address is http://www.landings.com. Intellicast is http://www.intellicast.com. Weathers is http://cirrus.spirl.umich.edu/wxnet. Go to the landing site and click on Weather under the Aviation directory. You'll find one of the most comprehensive weather sites around. Intellicast and Weather also offer valuable weather information. Figure 47. A friend of mine who's Hawaiian is fond of saying, "Here today, gone to Maui," which is true of most websites. They come and go. The above addresses were in good working order at the time of this printing. Keep in mind that while these sources offer excellent weather information, they don't necessarily constitute a legal weather briefing. They may not offer all the information necessary for pre-flight planning, such as NOTAMs. Use them as an additional service.
Hello, Americans. Shop Talk, page 2. There you have it. Rod is reluctant to make this book any bigger. Hopefully, you understand its salient features. In regard to this book being big, Rod wants you to know it's built that way for safety. In the event you can't clear the trees on the end of the runway during takeoff, pray that you have Rod's book with you. By opening the window and throwing out the book, you get an extra 500 foot per minute rate of climb. Now that's a safety advantage. Rod Machado, good day. Frequency change approved.
Chapter 14. Flight Planning. Getting there from here. Despite the navigational ease of certain cross-country trips, some pilots still manage to get lost. There are two major islands off the coast of Southern California, Santa Catalina and San Clemente. San Clemente is approximately 57 miles off the coast, and Catalina lies about half that distance. Catalina is a popular fly-in spot for many pilots. San Clemente is a naval base, not open to the public. Somehow, about twice a year, a pilot manages to land at San Clemente after mistaking it for Catalina. You might think the pilot would know something was wrong when it takes twice as long as expected to get to Catalina, and the runway doesn't have the same numbers. Such details aside, some pilots manage the feat, often while in contact with a Unicom operator on Catalina Island. By the way, Catalina is a non-tower airport. The conversation usually goes something like this.
Catalina traffic, this is 2132 Bravo. I'm on final to land. 32 Bravo, I don't see you, but there's no reported traffic for runway 24. Catalina Unicom, this is 32 Bravo. A jet just strafed me. 32 Bravo, there are no jets in the pattern. Then someone up here is flying a heck of a model airplane out here. I'm going to have to talk to somebody about that. It's dangerous. 32 Bravo, I don't see anyone flying model airplanes at Catalina. Well, I just touched down, and I bet it belongs to those two kids in Boy Scout uniforms walking over to my airplane. Well, shoot, they boys got guns. And now you know the rest of the story.
Mistakes happen. Contrary to popular law, the military doesn't make you enlist for 4 years either. They're pretty nice about it. Often they just talk with the errant pilot, show him all their guns and ammo, then suggest he might want to reread the chapter on flight planning to avoid making the same mistake again. To avoid having such a misadventure or worse, let's invest a little time in acquiring some flight planning knowledge. What is flight planning? Sometimes students get very involved with the details of flight planning. Up to their elbows in calculators and scratch paper, they often lose track of the reason they're crunching numbers. There's a lot more to flight planning than just plotting a course. Flight planning is information management. Your job is to assemble, interpret, and put to use all the information needed to safely make a flight from point A to point B. Here are some of the reasons you flight plan. To know how to navigate from departure to destination. To know if the weather presents any problems. To know whether there is any condition, such as weather, equipment, runway availability, etc., so adverse that you shouldn't go. To make certain there is sufficient fuel on board, with an adequate safety margin, to reach your destination, given the wind and other conditions en route. To enable you to file a flight plan, so that someone will begin looking for you if you don't reach your destination within a reasonable period. To determine if you, as pilot in command, and the equipment, aeroplane and accessories, meet all the demands of a particular flight. To identify any areas en route or at your departure or destination which require special consideration, such as mountains, preparation, short fields, or equipment, engine preheat in extreme cold, for example. To find out if the aeroplane can safely carry the load of people and fuel you're planning on taking, and whether the weight can be loaded in such a way as to meet certain limitations. More on weight and balance a bit later. To know whether adequate fueling facilities will be available en route or at your destination. To calculate how long the flight will take, and to determine whether you, your passengers, or your airplane will need one or more stops en route, and if so, where those will be. To determine whether the flight can be safely and successfully completed under conditions for which you are licensed and current. If you are not current for carrying passengers at night, will you arrive at your destination before dark, with enough of a time margin to allow for unexpected headwinds? If you don't have an IFR rating, will the flight definitely be in VFR conditions? If conditions are marginal, are you comfortable and capable of handling the aeroplane in such circumstances?
Flight planning is not an enormously complex task. It's really just information gathering and some calculation. In fact, planning a flight is often a favorite task of pilots who get to fly the flight, once on paper and again in the air. Properly done, flight planning is like buying an insurance policy for you and your passengers. Done poorly, or not done at all, it exposes everyone involved to unnecessary risks. It's my job to take risks, not yours.
Measuring direction. Once upon a time, sailors set out with nothing more than the sun, stars, and their senses to guide them. Today, you're in a more fortunate position. As a pilot, you have a wide variety of means for determining where you are and where you're going. Everything is somewhere. Keep that in mind next time you're lost. The challenge is in finding out where what you want is. Airports are in a fixed location, even in California despite all the earthquakes. We describe the location of airports and other things we want to find by their position on an invisible grid of lines called latitude and longitude, as shown in Figure 1a. These lines are not actually painted on the Earth, of course, but they are drawn on all navigational charts used by pilots. Lines of longitude run from the true North Pole to the true South Pole, as shown in Figure 1b. Think of longitude as something running the long distance from the top to the bottom of the Earth. Longitude lines are also known as meridians. Lines of latitude run sideways, like a sideways pass in football, a lateral pass. Lines of latitude are perpendicular to lines of longitude, as shown in Figure 1c. They run in an easterly and westerly direction around the Earth and are longest around the equator. Spaced 1 degree apart, 360 lines of longitude drop from the north to the South Pole, striping the globe. The longitude line running directly through Greenwich, England, is known as the prime meridian, the 0-degree longitude line. By convention, we start counting lines of longitude east and west from this point, as shown in Figure 2. To the left or west of the prime meridian are 180 lines of longitude, including the prime meridian. To the right or east of the prime meridian are another 180 lines of longitude, also including the prime meridian, 360 in all. Longitude is stated as being a certain number of degrees east or west of the prime meridian. You can see how the lines of longitude help us locate places on the Earth. Africa's west coast, for instance, begins near the 20-degree west longitude line. Central Africa appears to lie on the 20-degree east longitude line. While longitude lines are helpful, they don't quite serve to nail down a position, since 20 degrees west can still be anywhere from up near the North Pole to down near the South Pole. With the use of latitude lines, we can precisely locate our position. The 0-degree line of latitude, otherwise known as the equator, is located at the midpoint of the Earth. Spaced 1 degree apart, lines of latitude run parallel to the equator, spaced north and south. Latitude lines north of the equator are called north latitude, and south of the equator are called south latitude. They are sometimes called parallels because, unlike lines of longitude, latitude lines are parallel to each other, as shown in Figure 2. If you were standing at the center of the Earth, the angular distance from the equator to either pole would be 1/4 of a circle, or 90 degrees. Lines of latitude run from 0 degrees at the equator to 90 degrees at the poles, as shown by the smaller globe insert on Figure 2. The 90-degree north latitude line is a tiny little circle, a dot, sitting at the true North Pole. The 90-degree south latitude line is a small circle at the South Pole, a point on a polar bear's nose. The United States is located between 30 degrees and 45 degrees north latitude and 75 degrees and 125 degrees west longitude. See Figure 2. Any specific point on Earth can be referenced by lines of latitude and longitude. Washington, D.C., for example, is located at approximately 39 degrees north latitude and 77 degrees west longitude. Soon, we'll discuss how we achieve even more precise measurements with latitude and longitude, making it easy to find individual airports. Time measurement. A day is defined as the time it takes for the Earth to rotate 360 degrees, one full rotation. With 24 hours in a day, the Earth rotates 15 degrees every hour. 15 degrees times 24 hours is 360 degrees. If the Sun were directly over the prime meridian in Greenwich, England, it would be noontime for the English locals. But it would be very early in the morning for everyone on the U.S. West Coast. In fact, for everyone on the west coast of California, the difference in longitude between their location and the prime meridian is 120 degrees. This makes the time difference approximately 8 hours. 120 degrees divided by 15 degrees per hour is 8 hours. It's standard practice to establish time zones in the United States at 15-degree intervals, as shown in Figure 3. The center of each time zone is located on the 75th, 90th, 105th, and 120th meridians. These zones are respectively called Eastern, Central, Mountain, and Pacific time zones. Each zone has 1 hour time difference, 15 degrees per hour, from its neighbor. You would think the borders of different time zones would be straight lines running down the United States. Not so. Time zone borders usually consist of natural landmarks, rivers, canyons, etc. Local political reasons often explain why borders of each time zone are irregular rather than neat, straight lines. When the Sun is directly above the 120th, 105th, 90th, and 75th longitude line, it's noon in these time zones. For example, when the Sun is directly over the 90th meridian, it is noon Central Standard Time. Under Daylight Savings Time, however, noon occurs when the Sun is shifted 15 degrees to the left as an earthling looks up at it while facing south, to your right as you look at Figure 3. In other words, noon in the Central Daylight Time Zone occurs when the Sun is located directly over the 75th longitude line instead of the 90th. Daylight is saved since it's noon before the Sun reaches directly overhead. The day appears to last longer because the afternoon is longer. Daylight savings time is in effect from the last Sunday in April to the last Sunday in October, except in a few areas such as Arizona, which never goes on daylight savings time. As I said, Local politics is a factor. It's important to know about time zones for several reasons. First, the time listed on all weather charts is for Greenwich, England. This time is called Zulu or Universal Coordinated Time, abbreviated UTC. For any weather chart to be meaningful, you'll need to know how to convert from the time in Greenwich, Universal Coordinated Time, to local time. According to the conversion chart in Figure 4, if it's 1 p.m., 1300 hours, Pacific Standard Time, what time is it UTC? The chart says to add 8 hours. 1300 plus 800 is 2100 hours. It makes sense to add 8 hours to find the time in Greenwich, England, because it's always later there. If you're having trouble seeing how it's always later in England, examine Figure 5. When the sun is directly overhead in Greenwich, England, noon for them, it hasn't risen in the eastern sky of the U.S. It's still very early morning for us. Figure 4 is very useful for converting local time in any time zone to UTC when filing flight plans. All times on a flight plan are given in UTC. While filing flight plans requires local to UTC conversion, interpreting weather charts requires the opposite conversion. For instance, suppose the valid time of a weather report is between 0800 Zulu, UTC, and 1600 Zulu. When would this chart be applicable to you in the Pacific Standard Time Zone? To convert 0800 Zulu to 1600 Zulu to PST, do the opposite of what the conversion chart in Figure 4 suggests. Simply subtract 8 hours from the Zulu time. This gives us a local chart time of 0000 to 0800 hours, or midnight to 8 a.m. Between the end of April and the end of October, under Daylight Savings Time, you would subtract 7 hours instead of 8 hours. Most aviation operations are expressed by the use of the 24-hour clock. Starting at 1 a.m., the time is referred to as 0100 hours or 0100 Zulu, and 1 p.m. is called 1300 hours and spoken as 1300 Zulu. This count continues to the end of the 24-hour clock, with midnight being 2400 hours. A matter of degree, longitude and latitude on sectional charts. Individual lines of latitude and longitude allow us to precisely pinpoint any spot on a chart, like an airport. Figure 6 shows how we'd read these positions. Bob's Airport lies directly between the 93rd and the 94th lines of longitude, running up and down, and the 39th and 40th lines of latitude, running sideways. There's a great deal of real estate with a 1-degree boundary of longitude or latitude, so it's necessary to find a more precise means of determining a position. Every degree of longitude and latitude can be broken down into 60 smaller segments called minutes, as shown by scale A and B in Figure 6. We won't think of minutes as a time reference. For our purpose, think of minutes on a sectional chart as being similar to the smaller markings on a ruler. They simply let you physically locate your position between lines of latitude and longitude with greater accuracy. Imagine 60 smaller lines, each parallel to the 93rd and 94th lines of longitude running up and down the chart. Were the lines really there, you couldn't locate anything, because you wouldn't be able to see the chart. To solve the problem, chart makers place a small tick or line segment to one side, allowing you to see the subdivisions. The entire 30-minute longitude line, however, is there, helping give a rough division of the degrees of longitude running up and down the chart. Scale A clearly shows these smaller line segments, which make it easy to identify your position in degrees and minutes. In the same way, each degree of latitude has smaller minute segments as shown by Scale B, along with the 30-minute latitude line running across the chart between each degree of latitude. For greater accuracy, each minute of distance is broken down into 60 seconds, figure 6 left side. Although it's not possible for chart makers to show seconds on the chart, you can simply imagine their presence. As you can clearly see, Bob's Airport lies halfway between the 93rd and 94th longitude lines. It's located at 93 degrees 30 minutes west longitude and 39 degrees 30 minutes north latitude. Fred's Airport is located at 93 degrees 45 minutes west longitude and 39 degrees 50 minutes north latitude. Hanks Airport is located at 93 degrees 20 minutes west longitude and 39 degrees 25 minutes north latitude.
Well, there is a good chance all of your training as a student pilot will be done within the United States. If your instructor says to plan across country to Central America, she probably means somewhere in Kansas. Don't come back with a flight plan to Guatemala. It will make her very suspicious. Knowing that you'll always be flight planning for the U.S. helps, because it means you'll only need to consider west longitude and north latitude coordinates.
Let's identify specific airports by their latitude and longitude coordinates on a real sectional chart. Figure 7 is a sectional chart excerpt for Kansas. At the corners of each page, the latitude and longitude coordinates are circled. Of course, the 40-degree mark at the top left of the page can only be the 40-degree north latitude line, and the 94th degree mark can only be the 94th degree west longitude line. Remember, this is in the United States. Halfway between whole lines of latitude and longitude are the minute lines. The vertical and horizontal running lines marked on the chart in position A are the 30-minute lines I mentioned before. Take a look at Carrollton Memorial Airport at position B in the bottom center of the page. Carrollton lies on the 93-degree 30-minute line of longitude. What line of latitude does it lie on? Look at my drawn-in scale to the right of Carrollton. It looks like it lies at 39 degree 19 minutes north latitude. What is the latitude and longitude of Eagle Lodge Airport at position C? Eagle Lodge is located at 39 degrees 33 minutes north latitude and 93 degrees 15 minutes west longitude. What airport lies near the point defined by 39 degrees 54 minutes north latitude and 93 degrees 52 minutes west longitude? Yes, it's Longwood Airport, located at position D. Let's try one more. Identify the latitude and longitude location of Hawkins Airport, position E. It looks like Hawkins is located 10 minutes to the left of the 30-minute line running vertically down the center of the page. This would locate it at 93 degrees 40 minutes west longitude. Sometimes you have to just count individual minutes to the right or left from a whole line of latitude or longitude to find the minute value. The 5 and 10 minute marks are often difficult to see. The latitude of Hawkins is best found by counting down from the horizontal 30-minute line just above the airport. It looks like Hawkins lies halfway between the 26 and the 27-minute lines. Can minutes be subdivided? Yes, they can be divided into an additional 60 small, although very small, increments called seconds. They're too hard to see on this chart, but we can estimate that Hawkins lies on the 39-degree, 26-minute, 30-second north latitude line. Hawkins' coordinates would be represented as N 39-degree, 26-minute, 30 seconds, and W 93-degree, 40 minutes. You're probably wondering why I'm making such a big fuss about the latitude and longitude coordinates for an airport. Well, it's important since the newer methods of navigation, LORAN and GPS, all use latitude and longitude coordinates to determine airport position. You can usually navigate to an airport with your LORAN or GPS equipment by dialing in the airport's 3-letter stroke number code. Figure 8 is an excerpt from the AFD. It shows the latitude and longitude coordinates of both airports as well as the airport's 3-digit codes, shown in parentheses.
Now that you have an idea about how to find airports on a sectional chart, we're ready to jump right into basic cross-country navigation. But first, let me tell you about a friend. Now this is true. A friend of mine who had a golf ball hit his car's windshield. Surprisingly, he wasn't upset. He said it probably wouldn't have happened if he hadn't been driving on the golf course. Isn't this just like the pilot who got lost and actually said, it probably wouldn't have happened if the wind hadn't been blowing that day? You'll never need to worry about getting where you're going once you know the direction in which to aim the airplane and how to correct for the wind. This is the essence of basic navigation.
Cross-country navigation. As we saw before, there are several ways to get from one airport to the next. The most popular form of navigation is called electronic navigation. Devices such as VOR, LORAN, GPS, or VOR-based RNAV all allow you to navigate to your destination with relative ease. You might also recall our discussion on pilotage, in which you read the features, natural and man-made, on the ground and compare them to the map to find your location. This is also used in combination with dead reckoning, a term which stands for deduced reckoning and has no reference to what happens to pilots that don't know how to use it. Dead reckoning involves calculating the effects of wind and compass error on a plotted course. It is one of the most important forms of navigation. Why? Because it's the one form of navigation which requires you to understand how wind affects your aeroplane. There's no better education for a pilot than to have a mental picture of how wind affects an aeroplane. That's why I'll be placing the emphasis on dead reckoning and pilotage in this chapter. You're probably thinking, oh, come on, Rod. Why should I spend time learning about dead reckoning and pilotage when I'll probably use my GPS, LORAN, or VOR to get me to my destination? Stick with me for a few minutes, and you will learn to not just navigate, but to understand what you're doing and why. That will be worth its weight in aeroplane tires to you someday, no matter how you navigate. Understanding how compass errors and wind affects your flight has a profound effect on your ability to enjoy a lifetime of safe flying. Our trip. Let's start with the basics of how a course is plotted. The following are the 6 steps we'll use when planning a cross-country flight based on dead reckoning navigation. Flight planning step 1. Draw a line between airports or checkpoints. Flight Planning Step 2. Determine the true course. Flight Planning Step 3. Determine the wind correction angle. Flight Planning Step 4. Determine the true heading. Flight Planning Step 5. Determine the magnetic heading. Flight Planning Step 6. Determine the compass heading. While some, if not all, of your flights will use advanced forms of navigation such as VOR, GPS, or LORAN, good pilots always keep these basic steps in mind on every flight. As we follow each of these individual steps, we will fill in a flight log, Figure 9. A flight log is a means of keeping track of navigational information, not something to use in your aeroplane's fireplace. We'll only use a few of the sections in our flight log for this flight. Notice that the log starts with your checkpoints, Item 1, and leads you to the TC, or true course, Item 7. Eventually, it leads to the CH, or compass heading, Item 13, which is also Step 6 of our flight planning sequence. The point here is that the flight log provides you with a visual sequence of the basic steps you need to get to your destination airport. Let's fill it out as we proceed with each flight planning step. Flight Planning Step 1. Draw a line between airports or checkpoints. The first step in cross-country flight planning is to draw a line on the chart between our departure and destination airports. For this flight, we'll assume we're departing Table Rock Airport and our destination is AVA, Martin Memorial Airport, as shown in Figure 10. We'll draw a line between the centers of each airport symbol. If you're not planning a flight as a single straight course between airports, then draw lines between turning points. Treat each straight segment as an individual course and apply the following steps to each segment. Let's also insert these two airports as checkpoints in our flight planning form, as shown in Figure 11. Ideally, we'd pick several checkpoints for every flight. For simplicity, however, we'll only use the departure and destination airport in this example. Flight Planning Step 2. Determine the true course, the angle your flight path makes with the true North Pole. The first thing I like to do is to make a rough eyeball estimate of the course. From Table Rock to AVA, we're flying in a northeasterly direction, Figure 10. What do you think our course should be? Take a guess. I think it's somewhere around 50 degrees or so. These eyeball estimates are important and should be a prelude to virtually every flight planning calculation. Don't go looking for an answer until you have some idea of what it should be. Believe me when I say that good pilots are always making mental estimates about time, distance, fuel consumption, etc. When one of these estimates doesn't jive with their paper calculation, they recheck their work or put new batteries in the electronic flight computer. Follow this rule of guesstimating first, and I guarantee you will avoid some remarkably embarrassing moments in your aviation activities. Here's another of those handy rules of thumb. Any flight in a right-hand or easterly direction requires a true course of somewhere between 0 degrees and 179 degrees. Any flight in a left-hand or westerly direction requires a true course of somewhere between 180 degrees and 359 degrees. Figure 12 indicates that we need to fly an angle of 60 degrees with respect to the true North Pole on our flight from Table Rock to AVA. Conversely, for our return flight from AVA to Table Rock, we need to fly an angle of 240 degrees. the reciprocal of our original heading, with respect to the true North Pole. An angle is defined as a course. Since this course is relative to the true North Pole, we call it a true course, unlike some of the courses I had in college. This name allows you to understand the reference the angle is measured against. This is important because, as you'll soon see, there are magnetic courses and compass courses.
To measure the true course, find a line of longitude approximately halfway between the airports as shown by point A in Figure 10. When measuring any true course on a sectional chart, it's best to pick a line of longitude halfway between your departure and destination as shown in Figure 10, point A. We do this because all the lines of longitude converge at the North Pole and their angles change as they converge. A halfway measurement point is more than accurate enough for navigation. Remember, we're launching Cessnas, Pipers, and Katanas here, not cruise missiles. We only need to be accurate enough to be near the airport.
Put a dot where the course line intersects this line of longitude. Figure 13, point A, shows a close-up view of this intersection point. Now you're ready to use a simple but effective tool called a plotter. See Figure 14. If this looks remarkably like a grade school protractor, that's because it's remarkably like a grade school protractor. The top or curved part of the plotter is for measuring course angles. In the bottom center of the curved section, there's a small hole called a grommet. The bottom part of the plotter has several scales used for measuring distances on charts. We will discuss the different parts as we use them. Use the plotter's angle measuring device to determine your true course. Place the plotter's straight edge over the course line as shown in Figure 15. Slide the plotter up or down the course line so the grommet is over the small dot we made in Figure 13. You're done. Wait, come back here. You're done with the mechanics. All you have to do now is read the true course on the curved scale. Your true course is the number that lies directly over the line of longitude at the top of the curved scale. This line is shown close up in Figure 16, point A. It looks like 60 degrees is our true course for a flight from Table Rock to AVA Martin Memorial. In other words, 60 degrees is the angle your flight path makes with respect to the true North Pole. Since this is pretty close to our eyeball estimate of 50 degrees, we know it's an accurate, or at least plausible, measurement. Let's insert the true course of 60 degrees into our flight planning form, Figure 17. The plotter in Figure 16 has two scales, an outside scale, point B, and an inside scale, point C. The outside scale, the one with the E next to it, suggests we use this scale if we're going east or from left to right, which we are. The inside scale, the one with the letter W next to it, suggests we use this scale if we're going west or from right to left. Using the inside scale, you can easily see that the true course on our return flight is 240 degrees, the reciprocal of 60 degrees. 180 degrees plus 60 degrees is 240 degrees. One word of caution. The numbers on both scales increase and decrease differently than your intuition might suggest. Moving 3 degrees to the left of the plotter's numerical value of 60 degrees yields 63 degrees, not 57 degrees, violating our notion that things always get smaller to the left and larger to the right. It's printed that way because of the way the plotter is used. Read the scales carefully when measuring courses. Now you understand how to identify the direction of a course on a sectional chart. Next, we want to determine and correct, for the effects of wind, that might blow on our course. Flight Planning Step 3. Determine the wind correction angle. Before we can discuss how to correct for the effects of wind, let's review some basic principles about how wind affects your aeroplane in flight. Without wind, all you'd have to do is fly the compass course and you'd get where you're going. Mother Nature, trickster that she is not so accommodating. Wind exists to some degree almost every time you fly. If it blew directly on your nose or tail, it wouldn't blow the aeroplane off course. Nature, however, is perverse in tooth and law, and most of the time the wind blows at some angle to your flight path. The effect, left uncorrected, is to blow the aeroplane off its intended course. Your job is to compensate for this drifting tendency. If the wind is blowing from the north at 20 knots, we're saying the atmosphere is moving across the ground at a distance of 20 nautical miles for every hour that passes. If you were in a small hot air balloon and lifted off into this large moving block of wind, you would drift 20 miles in 1 hour's time, as shown in Figure 18a. Would you feel any wind blowing on you while moving? No, you are stationary within this moving block of wind. It's the block of wind that's moving. Stick your hand over the side of the balloon and the air is perfectly still. In fact, if you didn't look at the ground, it's unlikely you'd even know you were moving. Aeroplanes also drift with a moving block of wind, which is what inspired the Peter, Paul and Mary song, Blowin' in the Wind. In addition to this drift, however, they also have forward movement generated by their engines. The aeroplane in Figure 18b has a true airspeed of 100 knots, meaning it is moving at 100 knots through the block of air. It just so happens the block of air is also moving at 20 knots, and they are both moving in the same direction. The aeroplane's speed over the ground is a combination of the wind and air speeds. Adding our wind speed to our true airspeed gives us a speed over the ground, or the ground speed, of 120 knots. The aeroplane in Figure 18c moves through the block of air at 100 knots. With the block of air moving at 20 knots in the direction opposite that of the aeroplane, we have a net ground speed of 80 knots. 100 minus 20 equals 80.
If winds blew exactly on the nose or the tail of the airplane, it would be easy to determine your ground speed, but the wind usually blows at some angle to the intended flight path, making its effect on ground speed a little more difficult to determine. Even worse than its effect on ground speed, which only represents a delay in reaching your destination, is the fact that the wind is trying to push you where you don't want to go. This doesn't bode well for all those pilots who like ending up at the destination they had in mind. Remember, it makes the passengers nervous if you keep landing at unknown airports to find out where you are. Fortunately, we can correct for the effects of wind direction and velocity on our flight path.
The effect of water on a swimmer. Suppose the swimmer in Figure 19a wants to swim across the river from point A to point B. Unless he swims at some angle into the flowing water, he'll be carried downstream to point C, or out to sea. We'll call this the water correction angle, WCA. Figure 19b shows how angling into the current allows the swimmer to cross the river and arrive where he intended. Despite the fact our swimmer is pointed upstream, he actually travels directly across the river. Lights on, camera, action. Aeroplanes must do something similar when they travel in a stream of moving air. The effect of wind on an aeroplane. In Figure 20a, our aeroplane points in the direction of the desired course while flying with a left crosswind. Its track over the ground is a combination of the motion of the aeroplane and the motion of the air. The aeroplane is blown away from the desired course. The angle between the desired course and the actual ground track is called the drift angle. By determining the drift angle and correcting for it, you can fly a ground track exactly along the desired course, as shown in Figure 20b. Like our swimmer, you must head or point the aeroplane into the wind at enough of an angle to compensate for its effects. Instead of a water correction angle, we call this, remarkably, the wind correction angle. Determining WCAs is where that fancy electronic flight computer you purchased will earn its keep. However, you really can't sense what the wind does to your flight path unless you visualize how it blows on your aeroplane. This is why I insist you initially use, or at least become familiar with, the venerable and trustworthy E6B type computer to determine the wind's effect on your drift and ground speed. E6B, by the way, is an old military designation for the manual slide-type computer.
I know Rod sounds a little techno-regressed, but there is a reason he wants you to use the manual computer before you start crunching numbers with your Cray multi-megabyte handheld Captain Kirk Wind computer. Trust me on this one. Besides, this argument is eternal and probably dates back to Confucius's mom telling him to put down that abacus and use your fingers for counting.
I'll walk you through the steps needed to use the E6B for calculating a wind correction angle, but that's just the start of the calculations you can perform using this mechanical wonder. For an extended discussion on the workings and capabilities of the E6B, please take the time to read Post-Flight Briefing number 14-1. You'll need to know something about this to perform basic time, speed, and distance computations on the front side of the E6B. From now on, we'll refer to the E6B computer's two sides as the wind side and the front side. Using the wind side of the slide computer. Here's the wind and performance information for our trip. The wind, as reported by the flight service station for the altitude we'll fly, is 020 degrees at 40 knots. For this flight, our performance charts say our true airspeed is 100 knots. In Chapter 15, you'll learn about how to use performance charts. The true course from Table Rock to AVA is 60 degrees. Let's take just a second and visualize how the wind is affecting our aeroplane on this flight. See Figure 21. Notice that the wind is from 020 degrees. Our true course of 060 degrees means we're heading into a left quartering headwind. Common sense, always check for the presence of this when doing computations, indicates we'll need to correct to the left of 060 degrees in order to track the course line. It also indicates our ground speed will be something less than our true airspeed of 100 knots, since the wind is blowing on the front of the aeroplane. Given this, we have enough information to use our flight computer to determine two very important items necessary for all dead reckoning navigation: the wind correction angle, WCA, and our ground speed. Let's take a look at the wind side of the E6B type computer. Figure 22 shows the basic components of the wind side of a typical E6B computer. A rectangular sliding card fits inside the circular sleeve. The rectangular card has speed arcs with the appropriate values marked vertically along the center line. It also has diagonal lines running up and down the card. The circular sleeve has a movable inner scale that rotates about a center point, a small hole, known as the grommet. At the top of the circular scale is a small white triangular reference point known as the true index. At the very top of the rectangular card in Figure 23 are a series of 6 steps used in solving a wind problem. Before starting any problem, it's always best to slide the rectangular card up and down to place the card's 100 arc value under the grommet as shown in Figure 24. This makes it easier to do the measuring required. If your computer has been used before, the rotating circular scale probably has a complexion problem, lots of dots over its plastic face. If there are any pencil marks on this scale, it's best to erase them now, or there's no telling what kind of bizarre answers you'll get for your wind problems. Step 1 says to place the wind direction under the true index. Rotate the inside circle until 020 degrees is under the true index. Step 2 says to mark wind velocity up from the center. The center, by the way, is the grommet. Having placed the 100 arc under the grommet, simply count up the wind velocity along the given scale and make a mark. In our case, the velocity is 40 knots. Now, do you see why I had you place the 100 arc under the grommet? It simply makes it easier to count up to the specific wind value. Step 3 says to place the true course under the true index as shown in Figure 25. Notice that your wind mark is on the left side of the scale. Step 4 says to slide the wind velocity mark to the TAS, or true airspeed line, as shown in Figure 26. I simply move the cardboard slide upward until the wind mark is on top of the 100-knot true airspeed line. It's actually an arc because it's curved. You're done. Wait, come back here. You've got to stop running to the aeroplane every time I say you're done. All you need to do is read the ground speed and wind correction angle off the computer. Step 5 says to read ground speed under center, the grommet. Figure 27 shows a close-up of the center position. The grommet lies directly over a ground speed of 66 knots. Step 6 says to read the wind correction angle between the center line and the wind velocity mark as shown in Figure 27. Notice the small lines running diagonally down the sliding scale. Our wind mark falls on the 15-degree diagonal line to the left of the scale. Our wind correction angle is 15 degrees to the left. This means that a 15-degree angle to the left should compensate for the wind and allow us to track directly along the course line we drew on our chart in Flight Planning Step 1. Let's list the wind correction angle in our flight log as shown in Figure 28. I'll explain the significance of left and right WCAs in a moment. Now, look at how nicely all this ties together. Figure 29 is a comparison of our previous wind picture, Figure 21, and the computer's wind triangle. They're very similar, aren't they? That's because the computer actually solves wind problems by creating a small wind triangle. Post-flight briefing number 14-3 shows you how to construct a wind triangle for the flight from Table Rock to AVA Martin. Please take a good look at this briefing. It's well worth learning how to do a wind triangle. I sound like Confucius's mom, don't I? The reason we often don't construct wind triangles on charts is because it's easier to do them mechanically on the plastic face of the computer. Flight Planning Step 4. Determine the true heading. The next item in our flight log calls for the TH, or true heading. A heading is technically a course that's been corrected for wind. In other words, if you correct your true course for the wind correction angle, you obtain a heading that allows you to track directly along the course line you drew on the sectional chart. Given that our WCA is 15 degrees left, we need to subtract this from the true course to obtain the true heading for this flight. Why subtract? Anytime the aeroplane turns to the left, the numbers of the compass get smaller. A right turn causes the compass needles to get larger. It seems when most things are turned to the right, including radio dials, their numbers increase. Turning the dial to the left makes things less or smaller. That's why left WCAs are subtracted from the true course to obtain the true heading. Right WCAs are added to the true course to obtain the true heading. The flight log reminds you to do this by putting a minus sign next to L and a plus sign next to R. Our flight log shows that the true course of 060 degrees with a left WCA of 15 degrees gives us a true heading of 045 degrees as shown in Figure 30. Now that we have a true heading, is this all we need to get to our destination? Not quite. While a true heading corrects a true course for the wind, it's not something you can fly on your compass. In other words, the angles we've measured so far are in relation to the true North Pole. The aeroplane's compass is called a magnetic compass, not a true compass, because it points to a different pole. In other words, the magnetic compass measures angles with the magnetic North Pole, while we have measured angles on a sectional chart with respect to the true North Pole. We're mixing kiwi fruit and papayas here. Okay, apples and oranges. We need to correct the true heading for the difference, called variation, between these two poles. Let's find out how to do that. Flight Planning Step 5. Determining the magnetic heading. It's been said that women love a man in uniform. I believe this to be a substantiated fact. In fact, my wife fell for me because of the uniform. She couldn't resist the scarf, merit badges, and compass. And no pilot should be without a compass, even if you're out of uniform. As I said before, the compass is our primary means of navigation, but a slight problem exists, because the compass points to a pole that is different from the true North Pole. Recall that lines of longitude converge at the true North Pole. In earlier times, this was known to you as Santa Claus's house. The true North and true South Poles represent the spin axis points of the Earth. The Earth acts like a very large magnet, too big to put on any refrigerator, and has two magnetic poles, Figure 31. As I've previously stated, they are, unfortunately, not located in the same position as the true North Pole. Lying just a little north of Hudson Bay, the magnetic North Pole is separated by a distance of approximately 1,300 miles from the true North Pole.
The variation between these two poles presents a slight challenge in navigation. We measured our course with respect to true North Pole, but we must navigate using a compass that points to the magnetic North Pole. Fortunately, the answer is simple. Correct for the angular variation between the true and the magnetic North Poles. This is easy to do once you understand that this variation changes depending on your geographical location.
Figure 32 depicts an aeroplane in 3 different locations across the United States. In position B, The aeroplane is located so that the magnetic North Pole is directly in front of the true North Pole. In this instance, both poles appear in line with one another, so there is no apparent variation in location between poles. Your true heading would be a magnetic heading at this location, a location with 0 variation. You could simply fly the number you found with the plotter on the compass, assuming no wind, and the compass is free of errors itself. An aeroplane in position C views the magnetic North Pole to the west, in other words to the left, of the true North Pole. We have what is technically known as westerly variation between poles. The aeroplane in position A sees the magnetic pole located to the east, in other words to the right, of the true North Pole. Aeroplane A experiences easterly variation between poles. Clearly, the variation between poles depends on what part of the United States, or the world for that matter, you're in. Fortunately, we can correct for this variation since it's a known quantity dependent on your location. Figure 33 shows the angular variation between the magnetic and true North Poles. If you were flying along the western part of Texas, aeroplane C, the magnetic North Pole would be 10 degrees to the east of the true North Pole. Printed lines of variation shown on sectional charts are known as isogonic lines and are shown in Figure 34. They are spaced at half-degree increments and are marked for either east or west variation with an E or W, respectively. Iso, like isobar, means the same as. Gonic is a Greek derivative meaning angles. Anywhere along an isogonic line, the angular variation between the poles is the same. To the northwest of Florida, aeroplane E in Figure 33 is on an agonic line. The prefix A means no. Along the agonic line there is no angular variation between the poles. Standing along this line, the true and magnetic North Poles would be aligned with one another, and no variation exists in this location. The isogonic lines aren't straight because of the many slight variations of the Earth's magnetism, perhaps caused by too many heavy metal rock concerts in one area. Now you're ready to correct the true heading for the effect of magnetic variation. You can do this by finding the closest whole number, not half degree, isogonic line nearest the center of your course line, as shown in Figure 35. The magnetic variation is 4e, or 4 degrees east. Our flight log in Figure 36 shows that easterly variation is subtracted from the true heading to obtain the magnetic heading. If we subtract the easterly variation of 4 degrees from our true heading of 45 degrees, this gives us a magnetic heading of 41 degrees.
If we had westerly variation, we would have added this to the true heading to obtain the magnetic heading. An easy way to remember this is to think east is least, west is best. Least means subtract, best implies add. After correcting the true heading for variation, you now have an angle with respect to the magnetic North Pole or a magnetic heading. Now we have at least a number we can fly on our compass, right? Almost. There's one more thing to consider. What happens if the compass in our airplane is slightly inaccurate? In other words, what happens if the value it shows deviates slightly from the actual magnetic direction? We need to compensate for this deviation before we can set off on our cross-country flight.
Flight Planning Step 6. Determine your compass heading. Many instructors are fond of saying that compasses are devious devices. Occasionally, they lie. Some items in the aeroplane have a strong magnetic field that causes the compass needle to turn or deviate slightly, resulting in an error. If you think about it, the aeroplane has quite a few little things that can generate deviant magnetic fields: radios, lights, tools, magnetized metal parts, and flight instructors. Compass deviation is different for each aeroplane. That's why you always find a compass deviation card mounted near the magnetic compass, Figure 37. Have you ever noticed a painted compass rose? These are not decorated flowers that point north. Around the airport, much like the one shown in Figure 38, this isn't a sacred place where druids go for a belly button alignment. It's much more practical.
Mechanics place the airplane in the center of this compass rose and point the nose in precise magnetic directions painted around the circle. All the airplane's equipment is turned on to obtain the maximum amount of potential magnetic interference. The actual magnetic direction is measured against the compass indications. This process is known as swinging the compass. To the extent possible, adjustments are made to the compass to eliminate discrepancies. Any remaining deviation between the actual magnetic direction and what the compass shows is recorded on the compass deviation card, Figure 37. This card will usually be found mounted directly beneath the compass.
Step 6 of cross-country flight planning requires you to correct the magnetic heading for the compass deviation. To obtain a heading, you can fly on your compass. The compass deviation card in Figure 37 indicates that if you wanted to fly a magnetic heading of 060 degrees, you'd need to steer a heading of 057 degrees on your compass. In other words, with a value of 057 degrees showing in the window of your compass, you'd actually be making an angle of 060 degrees with the magnetic North Pole. The difference between the magnetic heading you want to fly and what's shown on the compass is called the compass deviation. In this case, the deviation is -3 degrees. As you see in Figure 37, the deviation can vary on different headings. What would the deviation be on a magnetic heading of 310 degrees? Since this value isn't listed, use the deviation for the magnetic heading closest to this value. In this case, a magnetic heading of 300 degrees is closest to 310 degrees. This deviation is +3 degrees, so we'd fly 313 degrees on our compass. Correcting the magnetic heading for the deviation gives us the correct compass heading. Since we want to fly a magnetic heading of 041 degrees, the closest value on the compass deviation card in Figure 37 is 030 degrees. The deviation on this heading is -2 degrees. We will steer 039 degrees on the compass, making the 2-degree correction, which lets us correctly fly 041 degrees. Enter this compass heading in the flight log, as shown in Figure 39. Phew! The flight log shows we have finally arrived at a heading to fly. This compass heading will take us from Table Rock to AVA Martin, correcting for wind, magnetic variation, and compass deviation. In these few short pages, you've learned the basics of dead reckoning navigation. Of course, we haven't found distances nor used our calculated ground speeds to estimate fuel consumption and time of arrival. We'll do that in a while. For now, understand that calculating the compass heading to be flown is an important part of every flight plan. If your flight has 2 or more legs, places where the course line drawn on the chart changes direction, then you'll need to calculate the compass heading for each leg. On longer flights, you may have several legs, with flight log items 6 through 13 completed for each leg. Once you get a little practice using the computer, you will do these calculations quite quickly. The basic process of dead reckoning navigation from Table Rock to AVA Martin involves finding a course, correcting it for wind to obtain a heading, then following the steps listed below. True heading, 45 degrees. Variation, -4 degrees east. Magnetic heading, 41 degrees. Deviation, -2 degrees. Compass heading, 39 degrees. Did you notice the first letters of each line? They are T, V, M, D, C, and they refer to the values of true heading, plus or minus the variation, equals the magnetic heading, plus or minus the deviation, equals the compass heading. Don't forget this letter sequence. It will help you remember how to convert a true heading into a compass heading. In fact, here is a great mnemonic to help remember this. Television makes dull company. Simply visualize yourself sitting in front of the TV planning a cross-country flight while thinking. Figure 40 shows this process using a flow diagram that we'll use from now on. You can also use the flow diagram in Figure 40 to obtain something known as the compass course, shown in Figure 41. A compass course is essentially a compass heading without the wind correction angle. Sometimes you will want to make a short flight, well within the aeroplane's fuel range, that doesn't require elaborate navigational calculations. You plan to use VOR, LORAN, or GPS to take you to your destination, and neither want nor need detailed flight planning and wind correction. That's fine. There's nothing wrong with this for those short hop flights. You simply start off toward your destination using the magnetic course, backed up with either pilotage or some form of electronic navigation. For longer flights that are sure to consume a lot of fuel, you need to do more detailed flight planning to determine ground speeds and fuel consumption rates. See Post-Flight Briefing number 14-4. Figure 41 also helps you determine your magnetic course. Do you remember FAR 91.159, the VFR cruising altitude regulation? This regulation requires you to fly at even or odd 1,000-foot levels plus 500 feet, depending on your magnetic course. The magnetic course is easily determined by correcting the true course for variation, as shown in Figure 41.